Hello there, and welcome to Life Beyond Seen, where curiosity drifts quietly across deep waters and science finds its calmest voice. Tonight, we're setting sail not across the oceans we know today, but across the ones that lived beneath the world of ice. Imagine a planet wrapped in cold breath, where continents stretched farther, winds were sharper, and yet beneath miles of frost and silence, the ocean never stopped moving. It pulsed and shifted, it whispered beneath frozen skies, and in its slow circulation life endured. I wonder where you're listening from tonight. Maybe it's a place far from the sea. Maybe the sound of waves is something you only hear in your memory. But no matter how far inland you are, there's salt in your blood that once came from the same water that filled those ancient basins. The ocean, even when buried under the weight of an ice age, was never gone. It simply changed its rhythm. If you find these quiet dives into the past soothing, if it helps you unwind or makes you curious about what the world once felt like, I'd be so grateful if you gave this a like, maybe even subscribed. It helps this little channel reach others who might need a moment of calm too. Now take a slow breath, let it settle. Because before we explore the deep waters that once lay beneath glaciers, before we imagine the whales that sang in colder seas or the coastlines that no longer exist, we have to step back, about 20,000 years or so, to a time when ice ruled the Earth. The Ice Age wasn't a single moment frozen in place. It was a long, restless pattern of glacial and interglacial rhythms, a slow pendulum between cold and less cold, where massive ice sheets crept down from the poles, grinding mountains and shaping valleys. During its height, roughly 20,000 years ago, the planet looked very different. Vast areas of North America, Europe and Asia were buried under ice kilometers thick. Sea levels dropped more than 100 meters below what we know now. The oceans shrank back from the edges of the continents, revealing lands that no living human has seen uncovered since. But even then, while the land lay silent under white deserts of ice, the ocean was alive. It's easy to imagine that the Ice Age ocean was simply colder, darker, and emptier, but that would miss the intricate story of what actually unfolded below the surface. The truth is, the cold didn't just freeze, it transformed. Every current, every chemical balance, every flicker of life adapted in its own quiet way. In those deep waters, the planet's heart kept beating. To picture it clearly, imagine the Atlantic Ocean, stretched wider by retreating shorelines, its surface chilled and dense. The cold air above it pulled heat from the waves, and that dense water sank, sliding along the seafloor like invisible rivers of salt and temperature. The circulation of the oceans, what scientists call the thermohaline system, depends on these differences. Cold, salty water sinks at the poles and flows slowly along the bottom toward the equator, while warmer, lighter water drifts back along the surface. During the Ice Age, this system still worked, but it changed its tone. Colder conditions strengthened the contrast. The deep ocean grew heavier, oxygen levels shifted, and carbon, an invisible player in the planet's climate, was stored away beneath the waves. The Ice Age ocean was a vast carbon vault. Today we talk a lot about carbon dioxide in the air, but much of the planet's carbon has always belonged to the sea. During glacial periods, the colder water absorbed more of it, locking it away in the depths. This kept the atmosphere clearer, cooler and drier. The ocean acted as a silent regulator, drawing breath for the planet. Every time temperatures dropped, the ocean's chemistry adjusted. Microscopic plankton, the tiny drifters that form the base of marine life, responded by building shells richer in carbon and calcium, and when they died, those shells fell like snow to the seafloor. Layer after layer, they recorded the pulse of the cold ages, creating a living memory that scientists can still read in the sediments today. Above, on the surface, the winds were fierce. With so much ice covering the continents, the balance of heat and pressure across the planet shifted. Jet streams moved south. Storms carved through the mid-latitudes, stirring the seas, pulling up nutrients from the depths. The surface waters of the Ice Age were often rich with life, particularly near upwelling zones where deep cold water met the air. These were places of abundance, where plankton bloomed in the pale sunlight of short summers, where fish gathered, and where larger creatures, seals, whales, even the ancestors of some of the species we know today, followed those migrations in an endless circuit of survival. Still, life in the Ice Age ocean was not simple. For many species, the world shrank as temperatures fell. Coral reefs, for instance, suffered greatly. They need warmth and light, and as the oceans cooled, tropical waters contracted toward the equator. Sea levels fell, exposing entire reef systems to air, drying them into limestone ghosts. Yet some corals endured in isolated refuges, small oases of warmth in an otherwise cold sea. They waited, in a sense, for the ice to let go. Meanwhile, on the continental shelves, those wide, shallow edges of the continents that now lie underwater, the story was different. When sea levels dropped, those shelves became vast plains. Rivers carved deeper channels through them, winding toward what were now distant shorelines. Coastal ecosystems shifted inland following the retreating waves. If you could walk across what is now the floor of the North Sea, you'd find yourself in a cold grassland, dotted with herds of mammoth and reindeer. It's strange to think that the sound of waves once breaking on English cliffs now crashes hundreds of kilometres away, where that drowned land lies silent beneath the tide. In the southern hemisphere, the oceans told their own tale. Around Antarctica, the ice extended far out into the Southern Ocean, forming massive shelves that sometimes broke away in floating chunks. These icebergs drifted north, melting slowly as they went, freshening the seawater and changing its chemistry. The boundary where this meltwater met the open ocean became a living front, teeming with plankton and krill. Whales followed, and seals and seabirds. Life concentrated along those shifting edges of ice, where the cold met the slightly less cold, where the balance of salt and sunlight created narrow ribbons of productivity. The Pacific too was transformed. With sea levels lower, the Indonesian archipelago connected into larger islands, reshaping the flow of warm tropical currents that usually help balance Earth's heat. The equatorial waters cooled slightly, and monsoon shifted. These small changes in ocean routes altered the entire climate of regions far beyond. The ocean has always been Earth's climate engine, and in the Ice Age it ran on a different fuel. But let's step back from the data for a moment and just picture it. The world was quieter. There were no harbours, no shipping lanes, no engines cutting through waves. The air was crisp, the skies pale, the light softer. In the far north, the sea was rimmed with ice that creaked and groaned as tides moved beneath it. Beneath those frozen lids, dark water pulsed, filled with slow-moving life, fish with antifreeze proteins in their blood, plankton that bloomed under faint sunlight, and strange, deep creatures that felt little difference whether the surface was frozen or free. The ocean, in a sense, didn't belong to the ice. The ice belonged to it. Even in the depths of the glacial cold, thermal vents continued to glow along the sea floor. There, at the spreading ridges where the planet's crust slowly opens, heat escaped from within the Earth. Chemosynthetic life thrived, entirely independent of the surface climate. Worms, bacteria, and strange white crabs lived off the energy of minerals rather than sunlight. They were, in a way, untouched by the rhythm of ice and thaw. It reminds us that the story of life is never one note. Even when half the planet froze, the deep sea remained warm with its own quiet fire. What's fascinating is how these conditions shaped the planet's memory. The sediments on the ocean floor from the Ice Age hold patterns like a diary of the deep, thin layers of fine dust carried by ancient winds, traces of pollen from tundra plants, shells of plankton, and even volcanic ash from eruptions that once darkened the sky. All rest together, compressed by time. Scientists studying those cores can trace every pulse of cold and warmth, every change in carbon, every breath the ocean took as it cooled and warmed again. It's humbling to think that the ocean remembers in layers while we count time in days. When the world froze, it didn't just cool the water, it changed the rhythm of salt. Ice is made from fresh water, so when massive ice sheets formed, they trapped enormous amounts of it on land. The ocean became saltier. This change affected everything from density to circulation to life. Some regions became hypersaline, especially where evaporation exceeded the small amount of precipitation the cold air could hold. In others, melting icebergs brought bursts of fresh water that briefly lightened the surface. The result was a patchwork of ocean chemistry, constantly shifting, balancing, recalibrating itself over centuries. It was a delicate system, and yet it endured. It's easy to underestimate how vast these changes were. The drop in sea level exposed roughly 8 million square miles of land, an area about the size of South America. Coastlines stretched far outward. Bays vanished. Coral reefs sat dry under wind and frost. The oceans covered less of the Earth's surface, but they grew deeper in places where ice's weight pressed down the continents. When that ice later melted, the land rebounded slowly, and the sea crept back over it. Even now, some parts of the world, like Scandinavia and Canada, are still rising from that ancient pressure, millimetre by millimetre each year. The ocean and the land have been dancing partners in this long, slow waltz of weight and release. In this frozen world, life adapted with quiet genius. The great whales, for instance, still swam through the cold seas, their migrations altered but not ended. Krill populations likely flourished around the edges of ice, feeding on the abundant phytoplankton that thrived during short bursts of light. Fish species evolved to withstand the chill, developing antifreeze proteins to prevent ice crystals from forming in their blood. Seals and penguins expanded their ranges, while others sought new refuges. The ocean became a cradle for endurance, not abundance, but the balance held. In every sense, the Ice Age ocean was not a dead world. It was a world at work. Its currents continued to sculpt coastlines, redistribute heat, and carve the underbelly of glaciers. It carried oxygen to the depths and nutrients back to the surface. It stored carbon and exhaled it again when the ice began to retreat. The ocean is never still, even when the surface seems silent. And in that silence there was also connection. The exposed seafloor linked continents in ways we can hardly imagine now. People and animals crossed land that today lies hidden beneath shallow seas. The ocean's retreat created corridors of movement, bridges that shaped migration and evolution alike. Every tide that fell during the Ice Age laid the foundation for how the world's species, including us, would later spread and settle. If you were standing on a cold shore 20,000 years ago, the horizon would have looked closer, the ocean darker, the sound of the waves duller, muffled by the cold air. But beneath that calm, the same physics that guide today's seas still held true. Salt and temperature, light and current, wind and water, all moved in slow, patient dialogue. The Ice Age ocean was not another ocean entirely. It was the same one, speaking in a lower tone. And now, as we drift forward through this story, we'll follow where that tone deepens. We'll step into the age when ice and sea shaped each other completely, when glaciers met waves and carved the edges of continents, when the ocean, though burdened by cold, kept its pulse alive. Because the story of that meeting, the meeting of frozen land and restless sea, is what defined the world that came after. When the world grew colder and the great ice sheets began their slow descent from the poles, the meeting of ice and sea became one of the planet's most powerful boundaries. It wasn't a fixed line, but a shifting frontier, stretching and retreating over thousands of years. The place where glaciers met the ocean was a landscape in motion, a frozen shoreline constantly reshaped by melting, carving and grinding. It was loud and alive, though in a way that human ears would barely recognize. Ice cracked like thunder. Waves boomed against walls of frozen cliffs, and beneath the surface 1,000,000 tons of fresh water poured quietly into salt water, changing its chemistry, its temperature, and its flow. That meeting between ice and ocean defined the Ice Age world. It was there, at those frozen coasts, that many of Earth's most dramatic transformations took place. The ocean's surface temperature fell, not evenly but in vast, uneven patches. Some regions were sealed under thick shelves of ice, where the sea froze hard enough to hold boulders the size of houses. Others remained open, dotted with drifting icebergs that glowed pale blue in the dim light. Beneath them, the sea was dark but not dead. Water moved slowly, pressed by the weight above, and life carried on in forms small, patient, and remarkably adaptable. Glaciers, enormous rivers of ice, flowed from the continents into the sea, carrying with them a history of the land they crossed. Rocks, dust, and sediment were ground to powder and dragged along until the glacier met salt water. There, the ice began to float, and as pieces broke away, what we now call calving, each iceberg became a messenger from the interior. As those icebergs drifted, they melted, releasing their cargo of stone and soil. Over centuries, they left thick blankets of sediment on the seafloor. These layers, spread across the world's ocean basins, still mark the pulse of the glacial cycles. Every deposit is a page in Earth's memory, written in sand and silt instead of ink. The ocean, in turn, shaped the ice. Waves undercut the floating shelves, thinning them from below. Warm currents, relatively warm at least, slipped beneath and melted the ice from the inside out. The boundary where the ice lifted from the seabed, called the grounding line, advanced and retreated with the seasons and the centuries. When the ice pushed forward, it scraped the seabed, gouging deep troughs and leaving behind long ridges of sediment. When it pulled back, the ocean flooded in, filling those scars with water and life. Today, sonar mapping of the Arctic and Antarctic seafloors shows the traces of those movements. Parallel grooves and ridges stretching for miles, the fingerprints of glaciers long vanished. The water that met the ice was dense, heavy, and cold. As icebergs melted, they released fresh water that floated above the saltier layers beneath, forming a delicate stratification. In those boundary layers, plankton and other microorganisms found temporary refuge. The thin mix of nutrients from melting ice and sunlight filtering through the surface made these regions unexpectedly productive. Even in a frozen world, food chains began here, where the coldest waters breathed faint life into the dark. Tiny diatoms and algae flourished in narrow bands of light, feeding krill and small fish, which in turn fed larger predators. The ice was both barrier and blessing, a gate that closed off much of the ocean but created new ecosystems in its shadow. To imagine the scale of this interaction, think of the Laurentide ice sheet in North America, a mass of ice that once stretched from the Arctic Ocean to what is now New York. At its edges, near the Atlantic, tongues of ice reached the sea and met the tides. When those glaciers calved, the resulting icebergs could tower hundreds of meters above the surface and extend far below it. They drifted south, sometimes as far as the latitude of modern-day Spain, trailing sediment and fresh water in their wake. Similar events happened around the edges of Greenland, Scandinavia, and Antarctica. Each iceberg was a small experiment in how land, air, and sea exchange energy. The release of so much cold fresh water changed ocean currents, slowed some of them, and sped others up. The system was always adjusting. Where the glaciers were grounded on the continental shelves, the seafloor bore the full weight of their movement. As the ice advanced, it crushed marine sediments, pushed ridges of mud ahead of it, and carved depressions that became fjords when the glaciers retreated. Many of the world's fjords, those deep, narrow inlets that cut into northern coasts, were formed by this process. During the Ice Age, they weren't the tranquil blue waterways we see today. They were choked with ice and sediment. cold water surging beneath floating tongues of glacier. When the climate warmed and the ice melted back, seawater flooded in, creating the dramatic landscapes of Norway, Alaska and New Zealand that we know now. The interaction of ice and ocean also altered the atmosphere. When cold, salty water sank near the poles, it drove the global conveyor belt of currents that circulated heat and nutrients across the planet. This process, known as thermohaline circulation, depends on a delicate balance of temperature and salinity. Too much meltwater from glaciers could disrupt it, freshening the surface and preventing it from sinking properly. Evidence from ocean cores suggests that such disruptions happened repeatedly during the Ice Age, triggering abrupt climate shifts. Some periods of intense melting may have even paused the Atlantic currents temporarily, cooling Europe and altering rainfall patterns worldwide. The sea and the sky were in constant conversation, though the dialogue played out over centuries rather than seasons. Under the ice shelves, life found surprising ways to persist. Scientists studying modern Antarctic environments have discovered ecosystems thriving in the perpetual darkness beneath hundreds of meters of ice. Bacteria, sponges and small crustaceans live there, surviving on nutrients carried by slow-moving water or chemical energy released from the rock below. It's reasonable to believe that during the Ice Age similar hidden communities existed, sustained by the faint pulse of the sea. These organisms didn't need sunlight. They lived on what the ocean provided through its endless circulation, proving that even the harshest barriers can shelter resilience. In open waters away from the ice, the ocean's surface reflected the changing winds. As the planet cooled, belts of high and low pressure shifted, and with them the direction and strength of major currents. The Pacific saw the weakening of its warm western boundary flows, and the Atlantic developed sharper contrasts between its north and south. Upwelling zones, where deep water rises to the surface, became hotspots of productivity. These regions supported dense populations of plankton and fish, which in turn drew larger animals. Whales travelled along these nutrient highways, following the rhythm of food and temperature. For them, the edge of the ice wasn't an obstacle, it was a guide. It's worth remembering that the ocean doesn't freeze all at once. Even in the coldest periods, there were layers of difference. Near the equator, warm currents still flowed, though slightly cooler than today. Tropical seas didn't turn to ice. They simply cooled enough to shift ecosystems. Coral reefs shrank in size, but mangroves and seagrass expanded along the lowered coasts. The boundary between ice and open sea wasn't a clean line. It was a long, jagged zone of transition, dotted with flows, melt ponds and shifting shelves. This complexity made the Ice Age ocean dynamic. Every change in the position of ice altered the chemistry, the currents, and even the colour of the water. The physical meeting of ice and ocean was also a meeting of sound. Imagine standing near one of those ancient coasts where a glacier met the sea. You would hear the deep groan of the ice shifting under its own weight, the sharp cracks of calving, the distant thud of waves breaking against the frozen edge. Beneath the surface, whales communicated through long, slow songs that could travel for hundreds of kilometres, their calls echoing through water layered with cold and salt. The ocean was not silent. It spoke through vibration, pressure and movement, carrying information across distances greater than any landscape could hold. Over time, as the glaciers advanced and retreated, they created patterns of expansion and release that reshaped coastlines. When ice pressed the land down, the ocean moved in to fill the space. When the ice melted, the land rebounded and the sea withdrew. This process continues today in places like Scandinavia, where the crust is still rising from the weight it lost 10,000 years ago. The memory of ice remains not just in the sediments, but in the very shape of continents. What we call shorelines are really temporary boundaries in a long ongoing negotiation between rock, water, and temperature. The ocean, though vast, responded sensitively to these changes. A small shift in salinity or temperature could alter its entire circulation pattern. During the Ice Age, the deep waters of the Atlantic were more isolated from the surface than they are now. Oxygen levels dropped in some regions, forcing marine life to adapt to thinner supplies. In others, particularly near upwelling zones, oxygen was abundant, supporting large populations. The balance was uneven, and yet, through all the instability, the system didn't collapse. It adjusted. The sea found new ways to move heat and nutrients, new routes for its currents, new rhythms for its life. One of the most remarkable effects of this interaction was the shaping of sedimentary landscapes beneath the waves. Where glaciers met the sea, they deposited vast amounts of material: gravel, sand, and clay. Over time, this built up submarine ridges known as moraines. These features acted like dams, influencing where the water could flow. Some trapped cold water in basins, creating pockets of unusual ecology. Others directed currents into new paths. The fingerprints of those ancient boundaries are still visible on the ocean floor, guiding even the modern movement of tides and nutrients. For the creatures that lived there, these shifts meant constant adaptation. Marine mammals followed the ice as it advanced, hunting along the edges where prey was concentrated. Fish populations migrated with temperature, moving toward the equator or deeper into the water column when the cold grew too sharp. Even plankton, microscopic and delicate, responded. Some species disappeared from regions where light was blocked by ice, while others evolved to take advantage of the changing chemistry. The ocean's ecosystems weren't static. They were flexible, capable of bending without breaking. The ice itself was not just a passive layer. It influenced the planet's reflectivity, bouncing sunlight back into space and maintaining the cold. But as glaciers carved and melted into the sea, they also released trapped gases, small pockets of ancient air sealed inside for thousands of years. Each bubble contained information about the climate of its time. Today, scientists drill into ice cores from Greenland and Antarctica to study those samples, reading the story of temperature, carbon dioxide, and even volcanic eruptions. Those gases, once released into the ocean and atmosphere, joined the planet's cycle again, linking past and present through chemistry. It's easy to imagine the Ice Age as a frozen stillness, but at the boundary where ice met sea, everything was moving. The ice advanced, cracked, and retreated. The sea rose, fell, and shifted its currents. The air changed with each alteration, carrying new storms and new calm. These weren't abrupt changes on a human timescale. They took centuries or millennia, but to the Earth, they were pulses of energy, constant and rhythmic. The planet breathed through its oceans, and the ice was simply one layer of that breath. Even as the glaciers carved their marks into the continents, the ocean was erasing and redrawing its own maps. The sediment plumes from melting ice spread for hundreds of miles, clouding the water with minerals that fed plankton blooms. When those blooms died off, their remains sank to the bottom, creating new layers of carbon-rich mud. Over time, those layers trapped vast amounts of carbon that would otherwise have warmed the atmosphere. In that sense, the meeting of ice and sea was one of the planet's great regulators, a system that balanced temperature through slow exchange rather than speed. Beneath the ice, deep ocean currents flowed as they always had, though perhaps with more weight. These bottom waters were cold, nearly freezing, and rich with dissolved carbon dioxide. As they spread across the ocean basins, they stored the memory of the surface conditions that created them. When they finally returned to the light, sometimes thousands of years later, they brought that memory back into the air. The ocean, through its circulation, carried the timeline of the Ice Age within itself. As the centuries passed and climates shifted, the line where ice met ocean began to move again. The glaciers slowly retreated, exposing land and allowing the sea to rise. Each time the ice pulled back, the ocean reclaimed what had been taken. But before that warming began in earnest, the world spent long millennia in balance, a frozen equilibrium where ice and sea coexisted. That balance was fragile, yet it lasted long enough to leave deep marks on the planet's geology and biology alike. If you could have watched it from afar, the Earth would have looked pale and serene, its poles gleaming white, its equator muted blue. But beneath that calm appearance, the boundary zones were constantly alive with motion, erosion, and creation. The meeting of ice and sea was not an end to life, but a transformation of it. Every flake of snow that settled on a glacier eventually melted into the sea. Every drop of that melt carried the story of mountains ground to dust, of winds that blew for centuries, of sunlight that barely reached the poles. When it joined the ocean, it became part of a system that has been in motion for billions of years, and that motion would not stop. In time, the ice would begin to withdraw. The sea would rise again, filling the valleys and plains it once abandoned. New coasts would form, new currents would emerge, and the ocean would remember every contour carved by the cold. But before that thaw began, there was still one more act in the long conversation between ice and water. The breathing of the colder earth itself, the circulation that tied together poles and tropics, air and sea, life and climate in one unbroken exchange. That slow rhythm, that planetary heartbeat, was what came next. As the frozen world settled into its long breath of cold, the ocean became the lungs of the planet. Every current, every layer of temperature and salt, every rise and fall of the tides moved in quiet synchrony with the air above. During the height of the Ice Age, the balance between ocean and atmosphere governed nearly everything. Winds carried chill from pole to equator, rain patterns shifted, deserts expanded, and forests retreated. The ocean, more than any glacier or wind, dictated how cold the Earth could become and how long that cold could last. When the great ice sheets covered vast portions of the northern hemisphere, the weight of all that frozen water altered the planet's very shape. The crust flexed downward beneath the ice, and as a result the ocean basins changed too. Water that might have lapped at old shorelines found itself drawn into deeper depressions. The world's rotation slowed slightly under the redistribution of mass. Even the tilt of the planet wobbled in small ways, changing how sunlight reached different latitudes. Each adjustment, though measured in millimeters or fractions of a degree, set off ripples through the climate system. The ocean absorbed those ripples, storing them as gradients of temperature and density that would persist for centuries. In these colder centuries, the surface waters cooled, thickened, and sank more easily. That sinking movement, happening mostly near the poles, is what drives the great conveyor belt of the oceans, the global circulation that carries heat and nutrients from one hemisphere to the other. During the Ice Age, this conveyor ran slower and deeper. The polar seas, covered in ice for much of the year, allowed only narrow windows for the exchange between air and water. When that exchange happened, it was intense. Cold winds stripped heat from the sea, causing dense water to plunge downward, dragging dissolved gases with it. The deep ocean became a vast storage vault for carbon dioxide, oxygen, and nutrients. It was a quiet process, but immensely powerful. The deep waters formed near Antarctica, and the North Atlantic began a slow journey that could last 1,000 years before resurfacing. Along the way, they collected traces of the world's chemistry. As they sank, they carried oxygen from the surface. As they travelled, that oxygen was consumed by the slow decomposition of organic matter falling from above. By the time those waters re-emerged, they had been transformed. This circulation cycle gave the Ice Age ocean a layered personality. Thin skin of oxygen, rich cold water above, a vast middle of sluggish nutrient-heavy deep water below. The layers rarely mixed, preserving the cold at the surface and locking away the warmth of earlier ages far beneath. The atmosphere responded in kind. With the ocean absorbing more carbon dioxide, the air grew clearer and drier. Less water vapour meant fewer clouds in some regions and more intense storms in others. Rain belts shifted southward, leaving once green regions to turn to steppe or desert. The Earth's breath became shallow and measured, each inhalation of warmth followed by a long exhale of cold. Yet even as the global climate tightened into this chill rhythm, regional differences remained strong. Some areas saw sudden thaws, others brief surges of snowfall. The ocean didn't enforce uniformity, it managed balance through variation. In the Pacific, for instance, the trade wind strengthened, pushing surface water westward and piling it up near what is now Indonesia. This created a steeper gradient of temperature across the ocean, intensifying the upwelling of cold, nutrient-rich water along the South American coast. Those upwellings fed immense blooms of plankton, the foundation of marine ecosystems. The Pacific during the Ice Age may have been cooler, but it was far from barren. Its productivity likely increased in many regions, drawing down even more carbon dioxide from the air. Each microscopic plankton cell, though alive for only a few days, contributed to this global exchange. When it died, it sank, joining the slow snow of organic matter that fed the deep. Meanwhile, in the Atlantic, the circulation pattern that today warms Europe through the Gulf Stream was altered. The conveyor still moved, but its northern branch was weaker and its southern flow stronger. Cold, dense water formed near the edges of the ice sheets and slid southward along the bottom, while warmer currents from the tropics struggled to penetrate northward beneath the persistent chill. The result was a steeper temperature gradient between hemispheres. Northern winters became longer, southern oceans slightly milder, and the winds that crossed the equator shifted their strength and direction. The planet's breath, once even, had become uneven, one lung working harder than the other. The cooling also reshaped the chemical dialogue between sea and sky. As cold water absorbed carbon dioxide, it changed acidity levels, affecting marine life that depended on calcium carbonate to build shells. Foraminifera, coccolithophores and other tiny organisms adjusted their biochemistry in response, altering the composition of sediments that would later serve as records for scientists. Even the colour of the ocean may have changed subtly. Cooler, nutrient-rich waters supported more plankton, giving the surface a greener hue compared to the clearer blues of warmer times. From space, had anyone been watching, the Earth might have appeared slightly darker, a planet veiled in cloud and chlorophyll. The deeper layers of the ocean were another world entirely. With the surface locked in cold, the abyss became a place of slow transformation. Oxygen levels declined in some basins, particularly the Pacific. As the sluggish currents limited renewal from above, bacteria adapted, using nitrate or sulfate instead of oxygen to break down organic matter. These processes released trace amounts of gases like nitrous oxide and methane, which sometimes escaped back into the atmosphere, adding faint warmth that countered the deep freeze. It was an intricate balance, one that required no design, only the natural feedback loops of physics and chemistry. Currents along the continental shelves became highways for sediment and ice debris. As glaciers advanced and retreated, they released torrents of meltwater that carried fine particles far out to sea. These particles sank slowly, blanketing the seafloor in layers of clay and dust. Each deposit recorded not only the rhythm of the ice, but also the strength of the winds that carried dust from distant continents. During the coldest periods, dust storms swept across dry valleys and deserts, depositing minerals into the ocean that fertilized plankton blooms. Iron, a rare but vital nutrient, arrived in tiny amounts through this airborne route, linking deserts to marine productivity. Even in a frozen world, distant systems remained connected. The interplay between ocean and atmosphere extended to sound and motion as well. Stronger winds generated higher waves, particularly in regions free of ice cover. These waves mixed surface waters, distributing nutrients and gases. Storm tracks shifted toward the equator, and cyclones formed in unusual places. Lightning flashed over colder seas, producing nitrogen compounds that fell as rain, further feeding marine ecosystems. Every process was part of a cycle. Ice locking water on land, the ocean compensating through salinity and depth, the air adjusting its currents to keep the balance. In the Southern Ocean around Antarctica, the effect of this global breath was even more pronounced. The circumpolar current, an unbroken flow of water encircling the continent, became one of the most powerful features of the Ice Age ocean. Driven by fierce westerly winds, it isolated the cold waters around Antarctica, preventing heat from reaching the ice shelves. This current acted like a barrier, keeping the continent locked in deep freeze while channeling nutrients around the southern hemisphere. Beneath the sea ice, blooms of microscopic algae grew on the underside of the frozen sheets. When those algae broke free each spring, they seeded the surrounding waters with life, feeding krill and the whales that hunted them. Even under the grip of global cold, the circle of life continued, delicate but unbroken. The slow rhythm of this colder Earth was not constant. It pulsed with feedback loops that occasionally tipped it towards sudden change. Volcanic eruptions injected ash into the atmosphere, reflecting sunlight and deepening the chill for years at a time. Small variations in Earth's orbit shifted the distribution of sunlight across latitudes, subtly adjusting seasons and triggering expansions or retreats of ice. The ocean recorded each event in its chemistry. Layers rich in sulfur or tephra mark ancient eruptions, while variations in isotopes of oxygen trace the temperature of the water in which marine organisms lived. These signals, preserved in shells no bigger than a grain of sand, now allow scientists to reconstruct the breadth of that era in astonishing detail. For living creatures, the consequences of this planetary rhythm were profound. The colder waters held more dissolved oxygen at the surface, which benefited fish and other aerobic organisms. But as productivity increased and organic material sank into the depths, decomposition consumed that oxygen, creating zones of scarcity. Life responded by diversifying in form and behaviour. Some species migrated vertically through the water column, feeding near the surface and retreating to depth for safety. Others adapted to low oxygen conditions, evolving slower metabolisms or symbiotic relationships with bacteria that could process alternative chemicals. The Ice Age ocean wasn't simply harsher, it was more varied, a mosaic of habitats shaped by the breathing of the Earth itself. Temperature differences between ocean layers also influenced the formation of sea ice. In winter, when the surface cooled and froze, salt was expelled from the forming ice, increasing the salinity of the water below. That dense brine sank, driving circulation that reinforced the global conveyor belt. Each freeze-thaw cycle acted like a heartbeat, pumping energy through the deep. These pulses governed the timing of climate events across the globe. When sea ice expanded, the Earth reflected more sunlight, reinforcing the cold. When it retreated, darker waters absorbed heat, nudging the system toward warmth. The rhythm was slow but steady, the kind of balance only a planet can maintain. Dust, wind, and water work together in subtle coordination. As glaciers scoured the land, they ground rock into fine particles that winds lifted into the atmosphere. Those particles drifted across oceans and settled on the surface, where they fertilized plankton blooms. The result was a feedback loop. More plankton drew more carbon dioxide from the air, cooling the climate further, which allowed glaciers to grow and produce more dust. For tens of thousands of years, this self-reinforcing cycle kept the planet in a stable chill. Only when warming began to outpace these processes would the balance tip toward the thaw. The colder Earth breathed more slowly but no less deeply. In that slowness, ecosystems adapted to the long rhythms. Migration routes for marine life stretched farther, sometimes following the moving edges of ice across whole oceans. Nutrient pulses from melting glaciers provided temporary bursts of abundance. Seabirds, though fewer in number, found reliable feeding grounds near the edges of upwelling zones. Even the chemical exchange between ocean and rock intensified as colder, more acidic waters eroded continental margins, returning minerals to circulation. Nothing was wasted. Every molecule found a path through the system. On land, the influence of the ocean's breath was felt through climate patterns. Cold seas cooled the air that passed over them, shaping rainfall far inland. Regions near the ocean experienced muted seasonal swings, while interior continents faced extremes of heat and cold. The contrast between oceanic stability and continental volatility defined the weather of the Ice Age. It was a world of slow-moving fronts and persistent winds, where storms might linger for weeks and calm could last for months. The ocean's capacity to store and release heat dictated these rhythms, turning its deep waters into a kind of memory bank for weather. One of the most subtle yet important roles of the ocean during this time was its control over greenhouse gases. While much of the carbon dioxide was locked away, methane, a more potent but shorter-lived gas, was stored in icy deposits on the sea floor. These methane hydrates formed under high pressure and low temperature, creating vast reserves of frozen gas. As long as the ocean remained cold, they were stable, but during brief warm intervals, some of these deposits may have released their contents, adding pulses of warmth to the atmosphere. These releases were temporary but significant, acting as reminders that the planet's systems are intertwined in ways both stabilizing and precarious. The global climate was not static, even in its coldest moments. Within the grand span of the Ice Age were shorter cycles, some lasting only centuries. Periods of relative warmth allowed the ice to retreat slightly, raising sea levels and invigorating ocean circulation. Then the cold would return, the ice advancing again, the sea drawing down. Each oscillation reshaped coastlines, ecosystems, and even human migrations. The ocean's deep currents carried these transitions like a slow drum beat, marking time in waves rather than years. If one could have followed a single molecule of water through this system, its journey would have been immense. It might have begun as snowfall on a glacier compacted over centuries before melting and running to the sea. From there, it could sink into the deep, carried south along the Atlantic floor, circulating through the Antarctic abyss, and eventually rising again near the Pacific equator thousands of years later. In that time, continents would have shifted slightly, climates would have swung through cycles of cold and warmth, and species would have adapted and moved. Each molecule was part of a story larger than any one epoch, the continuous breath of the Earth in motion. As the world approached the end of its coldest phase, the patterns that had held steady for millennia began to loosen. A slight increase in sunlight during northern summers melted ice more rapidly. Fresh water poured into the ocean, disrupting the delicate density gradients that drove circulation. The deep conveyor faltered. The planet's breath caught for a moment, uncertain. In the atmosphere, carbon dioxide levels began to rise, released from the warming ocean and thawing soils. The feedback loops that had once maintained the cold now began to unwind slowly, almost reluctantly. Yet even as change gathered momentum, the ocean's memory of the cold endured. Its depths remained chilled, storing the imprint of the Ice Age for thousands of years after the surface began to warm. That deep cold would continue to shape climate long into the future, influencing how quickly glaciers melted and how rapidly seas rose. The breath of the colder Earth lingered, softening the transition into the warmer world that would follow. And as that warmth began to spread, the ocean's slow exhale carried with it new possibilities. The ice receded, revealing lands that had slept beneath its weight. Rivers cut new paths to the sea. Nutrients long trapped in glacial sediment flowed outward, feeding blooms that painted the surface waters green once more. The rhythm changed, but the continuity remained. The earth had taken its long, deep breath, and now, with the faintest stirring of warmth, it began to release. The sea rose to meet that change, quietly at first, then more boldly. It reached into valleys that had been dry for millennia, reclaiming the ground where mammoths once walked. The boundaries between land and water shifted again, as they always had, driven by the same slow heartbeat of the planet. The cold was not gone. It simply moved deeper, stored in the ocean's layers, waiting for its next call. The breath of the colder Earth was steady, patient, and vast. It taught the planet how to move energy slowly, how to balance extremes, how to store memory in motion. As warmth crept back and the ice began to yield, That memory guided the transformation, ensuring that the next stage of the world would unfold not in chaos, but in rhythm. The ocean had kept time for the planet, and now it was ready to change tempo once more. When the ice was at its greatest reach and the ocean lay drawn back from the continents, the world's coastlines were almost unrecognisable. The sea had retreated hundreds of kilometres from the places it once touched, exposing vast plains that had not seen sunlight in millions of years. Rivers cut through new landscapes, and what had been shallow seafloor became grassland, marsh, or steppe. The planet's shape was redrawn by absence. These low shores and lost lands stretched around every continent, linking regions that today are separated by deep water. The fall in sea level was a direct result of all the water locked in the ice sheets. Each glacier that advanced over a continent stored enormous volumes of frozen ocean. The combined effect lowered global sea levels by about 120 metres on average, though in some places the difference was even greater. The Earth's edges grew outward, revealing a network of continental shelves that had long lain hidden. These newly uncovered lands were broad, flat and cold, shaped by sediments from ancient rivers and the grinding of previous ice ages. Their surfaces were barren at first, but quickly colonised by hardy plants and animals, moving outward with the shifting climate. If you could have walked across one of these exposed plains, the air would have felt dry, the wind sharp, the horizon immense. The soil underfoot was young and thin, made mostly of sand and silt deposited by retreating tides. In some places it was crossed by deep river valleys that had once been estuaries. Those rivers now flowed much farther to meet the distant ocean, carrying meltwater from the interior ice. Their deltas spread wide across the new coasts, building fans of sediment that stretched for kilometres. Where the land met the sea, the tide range was often extreme, because the shape of the continental shelves amplified the pull of the moon. The result was a landscape that changed not only over centuries but over every tide. Across what is now northern Europe, one of these plains connected Britain to the continent. Today it lies beneath the North Sea, but during the Ice Age it was dry land. Geologists call it Dogger Land, though at the time it had no name, only space and silence. It was a low-lying region of rivers, lakes and grasslands that supported herds of reindeer, mammoth and bison. People crossed it too, following game or seeking new hunting grounds. The distant sound of waves came not from where England's coasts are now, but from a line far to the east. As the climate warmed thousands of years later, melting ice raised the sea again, and Doggerland vanished beneath rising waters. For generations the shoreline retreated mile by mile until only the higher hills remained as islands. Eventually even those disappeared, leaving behind sandbanks where fishing boats now pass. The memory of that land survives only in sediments and the occasional bone dredged from the seabed. Similar stories unfolded all over the world. Between Siberia and Alaska lay Beringia, a broad expanse that joined Asia and North America. At its widest, it stretched over 1,000 kilometres from one coast to the other. The land there was cold but not buried in ice. It supported grasses, shrubs and the vast herds of animals that grazed them. Mammoths, musk oxen and horses moved across it in migration patterns that would later shape ecosystems on 2 continents. Humans crossed there too, though perhaps not in a single great wave but over many generations, following the food sources that thrived in that open plain. The ocean on either side was locked away as ice, leaving only narrow channels between the continents. When the sea returned, those channels widened, drowning the pathways and isolating the species that had once shared them. In Southeast Asia, the same process created the Sunda Shelf, a landmass that joined the islands of Sumatra, Java, Borneo, and the Malay Peninsula into a single continuous region. The climate there remained warm, though cooler than today, and the vegetation shifted with the changing rainfall. Rivers from the interior mountains carved valleys through the shelf, carrying silt to a sea that lay far beyond the current coastlines. The exposed areas were crisscrossed with floodplains that supported tropical forests and savannas. As the sea rose again, these lowlands were submerged, fragmenting ecosystems and isolating populations. Species of animals and plants that once shared a continuous habitat found themselves divided by new straits and gulfs. The distribution of life across modern Southeast Asia still bears the imprint of those drowned landscapes. To the south, the Sahel Shelf joined Australia, New Guinea and Tasmania into one vast continent. The exposed land bridged the gap between islands that are now separated by hundreds of kilometres of ocean. Humans reached this combined landmass tens of thousands of years ago, establishing settlements across the northern coasts and inland plateaus. When the ice receded and the sea returned, the people adapted to shrinking coasts, moving inland or to higher ground as familiar routes disappeared beneath water. The slow flooding took centuries, yet for those who lived through it, the change would have been tangible, a gradual but unstoppable transformation of home into horizon. Everywhere the sea withdrew, the earth revealed stories written in its sediments. Old coral reefs stood exposed and lifeless, their skeletons bleached by air and frost. Canyons carved by ancient rivers extended far out across the shelves, ending abruptly where the ocean floor dropped away. In the Gulf of Mexico, the Mississippi's valley ran more than 200 kilometers farther than it does now, cutting through what is now submerged continental margin. Off the coast of South America, the Amazon's mouth was an immense delta, stretching far beyond its modern boundary. These features, now hidden beneath mud and sand, mark the outlines of a world that existed only during the coldest times. The ecosystems that developed on these temporary lands were shaped by extremes. Winters were long and harsh, summers short but intense. Plants grew quickly during the brief warmth, then withered under frost. Animals migrated vast distances to follow the seasons. Predators trailed the herds, and scavengers thrived on what the cold left behind. The exposed shelves served as corridors for life, allowing species to move between continents and regions that are now isolated. This movement reshaped global biodiversity. When the sea rose again, those connections were severed, and evolution continued along separate paths. Many modern species still reflect those ancient divisions. The retreat of the ocean also affected weather. With more land exposed, the planet's surface reflected sunlight differently. Dry areas expanded, dust storms became common, and winds carried fine particles across oceans. This dust fertilized marine ecosystems, feeding plankton that helped maintain the cold climate by removing carbon dioxide from the atmosphere. The process linked land and sea in a loop of cause and effect. As the ocean fell, dust increased. As dust increased, plankton thrived. As plankton thrived, the planet cooled further. The exposed shelves, though barren to the eye, played a role in regulating the global climate. On some of these plains, freshwater lakes formed in depressions left by old river channels. They froze in winter and thawed in summer, supporting small ecosystems of hardy plants and animals. Migratory birds found resting places there, feeding on insects and fish before continuing along their routes. When the sea eventually returned, these lakes became bays and estuaries. Their sediments, rich in organic matter, were buried under new layers of marine mud, preserving traces of the life that once flourished above the tide. Scientists studying cores from these areas find pollen, spores and microfossils that tell the story of changing vegetation and climate. Each grain of pollen marks a year, each layer a season long gone. Human history is intertwined with these lost lands. Archaeological evidence from coastlines around the world suggests that people followed the edge of the sea during migrations, relying on its resources for food and navigation. When the ocean receded, those coasts moved outward, taking the fertile estuaries with them. Communities adapted by following the water, establishing new settlements farther from the old. Tools, hearths, and bones found underwater today are remnants of those shifting lives. They show that humans were not merely passive observers of these changes, but participants, adjusting their patterns to the planet's rhythm. For them, the rising and falling of the sea was part of the world's breathing, sometimes generous, sometimes harsh, always present. The exposure of new land also influenced the chemistry of the ocean itself. Rivers running across the shelves carried minerals and nutrients that were quickly swept into the distant sea. These inputs fueled blooms of plankton that altered the balance of oxygen and carbon dioxide. The shallower continental margins, now dry, stopped contributing organic material to the ocean floor, changing the distribution of sediments and the habitats that depended on them. The ocean's circulation patterns adapted once more, redirecting currents along the new coastlines. The shape of the continents guided the flow of water and with it the climate above. Glaciers at the edges of these plains continued to advance and retreat with the seasons. When they moved forward, they scraped the newly exposed land, pushing ridges of gravel and sand before them. When they melted back, they left behind scattered boulders and braided river systems. Meltwater streams carried fine silt far across the shelves, creating broad floodplains that supported vegetation in the warmer months. Over time, these alternating layers of glacial and fluvial deposits built the foundations of future coastlines. Long after the ice melted, the sea would erode those deposits, shaping cliffs and beaches that traced the memory of the cold. The pace of change was slow but relentless. Over thousands of years, the ice held the ocean captive, and the world learned to live with larger continents. But once warming began, the reversal came just as steadily. As glaciers melted, rivers swelled, and the sea began its return. The first signs were subtle: salt marshes forming in river valleys, tides creeping higher each year, coastlines softening under waves. The people who lived along those shores would have noticed the difference within a lifetime. Campsites that once overlooked plains gradually faced water. Trails that led to hunting grounds became flooded channels. The transformation of low shore to seafloor was gradual enough to adapt to, but inexorable all the same. The return of the sea reshaped ecosystems once again. As water flooded the shelves, marine life reclaimed the territory. Estuaries formed where rivers met the rising tide, becoming nurseries for fish and crustaceans. Mangroves spread in tropical regions, coral reefs colonized the new shallow coasts, and kelp forests took root in temperate zones. The nutrients left behind by decaying terrestrial plants enriched the water, triggering bursts of productivity. For a time, the meeting of land and sea created some of the most fertile environments on Earth. What had been grassland became bay. What had been forest became lagoon. The boundaries shifted, but life continued without pause. The geological traces of these transitions remain visible today. Seismic surveys reveal buried river valleys beneath modern continental shelves. In the Mediterranean, submerged terraces show where ancient coastlines stood. Off the coast of Florida, limestone ridges mark the edges of reefs that grew when the sea was lower. In Australia, drowned dune fields and sinkholes map the paths of rivers that once crossed the exposed shelf. Each discovery adds another detail to the picture of how the Ice Age ocean sculpted the present world. Even after the sea returned, the Earth's crust continued to adjust to the weight it had lost and regained. Regions that had been pressed down by glaciers slowly rose, while those newly covered by water sank. This movement, known as isostatic rebound, continues today in parts of Canada, Scandinavia and Alaska. The process changes relative sea levels, lifting old beaches high above current tides or submerging others. It is another reminder that the planet's surface is never truly fixed. Every shoreline is temporary, a momentary balance between water, rock and ice. The memory of the low shores persists not only in rocks and sediments, but in human imagination. Myths from coastal cultures around the world speak of floods that swallowed lands or gods who pushed back the sea. These stories, passed through generations, may preserve echoes of the real events that accompanied the end of the Ice Age. Rising seas would have reshaped coastlines over centuries, erasing familiar landmarks and forcing migrations. The gradual but unstoppable nature of those changes left an imprint on memory, one that survived long after the waters stabilized. Scientists studying modern sea level rise often look back to this period for guidance. The rates and patterns of flooding that followed the last glacial maximum provide clues about how oceans respond to melting ice today. In those ancient transitions, the world saw how quickly the balance between land and sea can shift. It also showed how resilient life can be, finding new niches as old ones disappear. The return of the sea after the Ice Age was not a catastrophe, but a reorganization of the planet's surface, an adjustment to a new equilibrium that would last until the next major change. Beneath the waves that now cover those lost lands, the ocean still carries traces of their existence. Currents follow the contours of submerged valleys, eddies form over buried hills, and marine creatures migrate along paths shaped by ancient topography. The seabed is not featureless. It is the ghost of a former continent. Every ridge and hollow tells of rivers that once ran free, of forests that swayed in cold winds, of animals that grazed under pale sunlight. The ocean has reclaimed them, but it has not erased them. They remain, quiet and unseen, part of the foundation of the modern sea. As the world moved from its coldest phase toward gradual warmth, these submerged histories became the seed for the next chapter of Earth's evolution. The rising water redistributed heat and moisture, fueling new climates and biomes. The boundaries of continents changed once more, but the lessons of those low shores endured. The planet had learned how to breathe through cycles of ice and flood, how to reshape itself without losing balance. The sea's return was only the continuation of a process that had begun long before and would continue long after. The ice still lingered in the high latitudes, holding fast to its last strongholds, but its retreat was certain. The oceans swelled in response, spreading into every valley they had once abandoned. The sound of waves returned to cliffs that had stood silent for thousands of years. The winds carried salt again across the plains, and seabirds followed. What had been land became memory. What had been memory became sea. Yet the ocean, having reclaimed its ground, was not done changing. The warmth that drew it forward would continue to shape its movement, stirring currents, melting ice, and filling the air with new moisture. The world that rose from those lost lands would not be the same as the one that froze them, but it would remember them in its depths, as all oceans do. And as the sea spread once more across the continents, the balance of the Earth shifted again. The planet's long breath, drawn in during the cold, began to exhale. The waters that had waited in silence moved outward, touching the edges of continents that had forgotten their sound. In that slow return, the ocean prepared for its next rhythm, the steady, complex circulation that would come with the warming Earth, the pulse that would carry the planet from the age of ice into the age of rising tides. As the seas crept back over the wide plains left behind by the retreating ice, the water filled not just the valleys and river mouths, but entire continents' worth of corridors carved by time. These submerged paths became the hidden highways beneath the waves, the same ones that had once carried herds and people across the exposed shelves. When the rising tide reclaimed them, the world's geography was quietly rewritten, connecting some regions and severing others. Beneath the new oceans lay the faint outlines of those lost crossings, still guiding the movement of water, sediment, and life. When the last great glacial period was ending, sea levels rose unevenly. In some places, the ocean advanced quickly, flooding low basins and shallow coasts. In others, it lagged, trapped by ice or blocked by land still rebounding from the weight of glaciers. The result was a patchwork of new channels and submerged valleys, some stretching hundreds of kilometres, others just narrow gaps between mountains now turned to islands. The Earth's continents were no longer what they had been. Asia and North America drifted apart as the Bering Land Bridge drowned beneath cold northern seas. Europe lost its connection to Britain as Doggerland slipped away. Southeast Asia fractured into an archipelago, and the vast shelf that had joined Australia and New Guinea split into separate land masses. The hidden highways that had once linked people and animals became the foundation for ocean currents, migration routes, and ecosystems unseen from the surface. Underneath the water, these drowned corridors formed natural channels that guided the flow of tides and currents. Rivers that had once wound across the exposed shelves continued to influence the shape of the sea floor. Their ancient beds became submarine canyons, directing sediment from the coasts into deeper waters. Along the margins of the Atlantic and Pacific, these canyons carved paths down the continental slope, some extending thousands of meters below the surface. Today, many still carry turbidity currents, dense flows of sediment-laden water that surge through the deep, building vast fans of mud and sand on the ocean floor. These fans, invisible from above, are the fingerprints of the lost river systems of the Ice Age. In the Atlantic, one of the most prominent examples lies off the coast of North America. The Hudson Canyon, which begins near the modern coast of New York, once extended across a wide plain that is now submerged beneath the continental shelf. During the Ice Age, the Hudson River flowed through this valley to meet the distant sea. As the ice melted and sea levels rose, the canyon flooded, but its form remained. Now it acts as a channel for deep currents that carry nutrients from the shelf to the open ocean. Similar structures line the margins of every continent, silent continuations of the rivers that once cut through the glacial plains. Each is a reminder that the landscape of the ocean floor is a record of the world that came before. In the north, the flooding of Bering Year transformed the climate and ecology of two continents. When that broad plain connected Siberia to Alaska, it had acted as a bridge for animals and humans. As the sea rose, it became the Bering Strait, a narrow passage where the cold Arctic Ocean meets the Pacific. The water flowing through this strait plays a crucial role in global circulation. It controls the exchange of heat and salt between the two oceans, influencing weather across the northern hemisphere. The transformation from land to water created a new dynamic. The migration of species gave way to the migration of currents. What had once been a road for mammoths became a conduit for the planet's cold breath. The same pattern unfolded elsewhere. The straits that separate Indonesia's islands today, Makassar, Lombok and others, were once valleys and lowlands of the Sunda Shelf. When these flooded, they became narrow channels through which warm Pacific water now flows into the Indian Ocean. This exchange, part of what scientists call the Indonesian throughflow, regulates global heat distribution and affects monsoon systems across Asia. The drowned land beneath those tropical waters, once home to forests and rivers, now acts as a vital artery in Earth's circulation. The planet's climate depends on the pathways opened by that ancient flood. Farther south, the split between Australia and New Guinea reshaped the region's ecosystems. The shallow Torres Strait that now separates them was once a low, marshy corridor of mangroves and grasslands. When it filled with seawater, the connection vanished, isolating species that had once shared common ground. Birds and reptiles found themselves cut off, evolving along separate lines. Humans too saw their world divided. Yet the sea that replaced the land became its own connector, carrying fish, coral larvae, and nutrients between coasts. Even in separation, the ocean maintained continuity. The hidden highways of the sea did not erase connection. They changed its form. Along the western coasts of Africa and South America, where strong currents sweep north and south along the edges of the continents, the newly flooded shelves created broad, shallow zones of upwelling. These regions, where deep, cold water rises to the surface, are among the most productive ecosystems on Earth. The same geography that once supported Ice Age grasslands now fuels marine food chains. The Benguela Current off Namibia and the Humboldt Current off Peru both trace their origins to the seafloor contours left by ancient river valleys. The winds that drive them follow the same patterns that once carried dust from deserts into the sea. the ghosts of the old land still guide the new ocean. When scientists map the seafloor today, they find these patterns everywhere. Ridges where ancient dunes once stood, depressions where lakes lay frozen under ice age skies, channels carved by meltwater torrents. Some of the deepest submarine canyons cut through the continental margins of the Arctic, formed by rivers that drained the ice sheets. Others lie beneath the Bay of Bengal, where the Ganges and Brahmaputra once flowed far beyond their modern deltas. The sediments that fill these canyons are thick with the history of erosion, each layer representing a pulse of melting or advance. They show how the Earth's surface, even underwater, keeps the memory of its former shapes. These drowned landscapes also influenced human history in ways that are only now being understood. The submerged valleys and plateaus off the coast of India, for example, may once have supported early coastal communities. Off the western coast of India lies the Gulf of Khambat, where sonar surveys have revealed traces of what might be ancient river systems and possible human artifacts now buried under silt. Similar discoveries have been made off the coasts of Japan, the Mediterranean and the Americas. The idea that much of early human settlement occurred along coasts that are now underwater changes how we think about our past. The sea that hides these places has preserved them as time capsules, sealed by sand and silence. The flooding of the lowlands also altered the migration of animals. Species that had roamed freely across connected continents found themselves confined to islands. Others adapted by swimming or flying between new coasts. Marine mammals like seals and sea lions expanded their range into newly formed coastal environments, while fish populations shifted along the new current systems. The underwater highways became migration routes for life that would never see land again. Over time, these patterns became stable, forming the basis for modern marine biodiversity. The movement of water through these channels also shaped the chemical balance of the oceans. As currents began flowing through narrow straits and over shallow shelves, they mixed surface and deep waters more efficiently. This mixing distributed oxygen and nutrients, influencing the productivity of marine ecosystems. It also affected the storage of carbon dioxide in the deep ocean, playing a role in stabilizing the planet's climate after the end of the Ice Age. The geography of the seafloor, sculpted by ancient rivers and glaciers, became an integral part of the Earth's regulatory system. The hidden highways beneath the waves also serve as archives of geological change. Sediments that accumulated there capture the story of how the planet moved from ice to warmth. Layers of fine silt record the steady retreat of glaciers, while coarser sands mark sudden floods of meltwater. In some places, entire deltas are preserved under marine mud, their shapes still visible in sonar images. These features allow scientists to trace the sequence of events that led to the modern coastline. Every ridge and channel tells of a moment when water and land traded places. The transformation of these landscapes was not a single event, but a process that unfolded over millennia. The rising sea advanced in fits and pauses, sometimes halting for centuries before surging forward again. During these pauses, coastlines stabilized temporarily, allowing vegetation to grow and animals to adapt. Then, as another pulse of melting occurred, the waters rose once more, submerging what had only just become familiar ground. The result was a world in constant transition, where no generation lived on quite the same map as the one before. For early humans, these changes would have shaped routes of migration and trade. Coastal peoples followed the shifting shorelines, exploiting the rich resources of the estuaries and tidal flats. As sea levels rose, they adapted by moving inland or building new methods of travel across the water. The earliest evidence of seafaring likely comes from this period, when crossing short distances between islands became a necessity. The same instinct for movement that once drove migrations across land bridges now found expression in navigation across the flooded ones. The hidden highways beneath the waves may have inspired the first real awareness of the ocean as a path rather than a barrier. Even now, the topography of those submerged routes influences the way water moves. Deep currents follow the same channels that rivers once carved, and eddies form around submerged ridges and plateaus. The ocean's circulation patterns are not arbitrary. They are shaped by the architecture of the drowned world beneath. The Gulf Stream, the Kuroshio, and other major currents trace paths determined partly by these ancient features. In this sense, the Ice Age continues to guide the modern sea, its influence hidden but constant. There is also an element of continuity in how life uses these paths. Migratory species follow temperature gradients and current lines that often coincide with the shapes of the old land. Tuna, whales, and seabirds all rely on predictable flows of water and food that arise from the interaction between currents and underwater topography. In the Pacific, the deep channels between islands act like highways for marine life, concentrating plankton and fish along their edges. These routes, established after the flooding of the Ice Age plains, have persisted for tens of thousands of years. The living world adapts, but it does not forget the structure of its environment. The sea itself carries reminders of the land it replaced. In the sediment that drifts through the deep, traces of pollen, charcoal, and spores appear. Materials blown from vanished continents and forests. Each particle tells of an ecosystem that once stood above the tide. The ocean floor has become a vast archive of terrestrial life, storing fragments that drifted out to sea before the flood. Over time, these remnants mix with marine deposits, blending the history of land and water into a single continuous record. In the modern era, technology has begun to reveal these hidden landscapes in remarkable detail. Sonar mapping, underwater drones, and seismic imaging have shown us the contours of the seafloor with a clarity unimaginable a generation ago. We can now see river channels that wind through the deep Atlantic, dune fields preserved under the Indian Ocean, and mountain ridges that mark the boundaries of ancient continents. Each discovery adds another piece to the puzzle of how the Ice Age shaped our planet. The ocean, once thought to be a featureless abyss, turns out to be as varied and intricate as the land above it. Understanding these underwater highways is more than a matter of geology. They explain why currents flow where they do, why climates form patterns that persist across millennia, and why life concentrates in certain places. The sea's hidden geography is the framework for everything that happens within it. When warm and cold waters meet along these ancient contours, they create the upwellings that feed fisheries, the eddies that mix nutrients, and the pathways that link distant ecosystems. The drowned valleys of the Ice Age are still shaping the world we know. As the climate continued to warm after the last glacial maximum, the process of flooding slowed. The great ice sheets had melted back toward the poles, and the oceans approached their present levels. But the hidden highways remained active, their influence woven into the fabric of the planet's circulation. The sea, now fully in motion, had inherited the memory of the land it covered. Beneath the calm surface lay the outlines of a former world, its ridges, plains, and rivers repurposed as channels for currents, carriers of heat, and guides for life. The story of these submerged routes is a reminder that nothing on Earth is ever lost completely. The ice sculpted the land, the sea claimed it, and together they created a map that still defines our climate and our biology. The highways beneath the waves are not relics of the past. They are the foundations of the present ocean, unseen but indispensable. They connect continents not through rock and soil, but through water and motion. They carry the legacy of the Ice Age forward, turning what was once separation into connection again. And as the sea continued its rise, filling the last of the low basins and smoothing the edges of the continents, it began to find its balance once more. The circulation of the oceans settled into new patterns, the temperature gradient stabilized, and the memory of ice gave way to the rhythm of warmth. But the shapes carved by those hidden highways remained. They still lie beneath us, directing the world's great currents, storing its sediments, and whispering the story of when the land and sea traded places. The ocean, even now, moves according to their design, carrying the past forward into every wave. Beneath the cold surface of the glacial seas, the weight of ice was always at work. It shaped the face of continents and carved deep into the ocean's edge, leaving marks that would outlast the very climate that made them. The glaciers that covered so much of the world were not just passive sheets of frozen water, they were engines of construction. They ground rock to dust, carried it across valleys, and released it into the ocean in endless cycles of freezing, melting, and motion. The seafloor that exists today, the contours of continental shelves and slopes, the ridges, the plains, even some of the trenches, all bear traces of the work that ice performed in silence. While the Ice Age seems distant, the evidence of its architecture lies everywhere beneath the water. As glaciers advanced toward the coasts, they pushed massive amounts of rock and sediment before them. Some of this material was bulldozed into ridges that marked the glacier's maximum reach. When the ice began to retreat, those ridges were left behind, forming long arcs of gravel and sand known as moraines. Many now lie below sea level, forming underwater barriers that shape tides and currents. The coastlines of northern Europe, Canada, and parts of the southern hemisphere still show their influence. In Norway, where fjords cut deep into the mountains, and in the Canadian Maritimes, where submerged ridges line the seabed, the hidden architecture of ice remains intact, holding the memory of a colder world. Glaciers are not static masses of frozen water. They move like slow rivers of ice, creeping under their own immense weight. As they move, they scrape across the land, eroding everything in their path. Rock faces are polished smooth, valleys are widened, and deep grooves are cut into the bedrock. When the ice reaches the sea, it floats and begins to break apart, releasing the load it has carried. Each iceberg that calves from the glacier carries with it pieces of the land, stones, silt, and dust. As the ice drifts and melts, those materials rain down to the ocean floor. This process, known as ice rafting, distributed sediments across thousands of kilometres. On the seafloor, these dropstones can still be found, resting in layers of fine mud, far from any possible source of land. A single boulder the size of a chair might sit in the middle of a smooth, featureless plain, its presence marking where an iceberg once paused and melted in ancient seas. The accumulation of such sediments created vast deposits that later became part of the continental margins. In regions like the North Atlantic, these layers can be several kilometres thick, compacted under the weight of later deposits. The pattern of these layers, alternating coarse and fine materials, records the rhythm of the glacial cycles, times of advance and retreat, of ice loading and release. Each layer is a fingerprint of climate, a record of how the Earth's temperature and circulation shifted over tens of thousands of years. Scientists studying sediment cores from the deep ocean use these sequences to trace the pulse of the Ice Age, reading its story in grains of sand and silt instead of words. The action of ice on the seafloor went beyond erosion and deposition. In many places, glaciers extended far out onto the continental shelves, pressing down with such force that they reshaped the crust itself. Under that pressure, the land flexed and sagged, forming broad basins that would later fill with seawater as the ice melted. Some of these basins are now the great fjords and inlets that line the coasts of Norway, Chile, and Alaska. Others lie completely underwater, invisible except to sonar, yet they still influence the way the sea moves. Water trapped in these depressions circulates differently from the open ocean, creating microclimates of temperature and chemistry that persist even now. The Antarctic continent provides one of the best examples of how ice can build as much as it destroys. Beneath the massive ice sheet that still covers it, there are mountain ranges, valleys, and lakes sealed from the surface for millions of years. As glaciers flowed toward the coast, they scoured away rock and deposited it offshore, building large submarine ridges that now support the floating ice shelves. These ridges act as anchors, holding the ice in place and slowing its movement toward the sea. When scientists map them with radar and sonar, they see evidence of multiple cycles of growth and collapse. Each ridge marks a period when the ice was stable, followed by a retreat, and then another advance. The Antarctic shelf is layered with these features, silent testimonies to the planet's capacity for repetition and renewal. Farther north, in the Arctic, the same processes shape the seafloor in the Barents and Kara Seas, around Greenland and off the coast of Canada. There, ice streams, fast-moving corridors of glacier within larger ice sheets, acted like conveyor belts, transporting enormous volumes of sediment to the sea. At their mouths, these sediments piled up into submarine fans, broad cones of material that spread out from the edge of the continent. Some are hundreds of kilometers across. Over time, they became foundations for new ecosystems, their surfaces colonized by corals, sponges, and other bottom-dwelling creatures. The structures built by ice thus became the scaffolding for life, long after the ice itself was gone. Even the chemistry of the ocean bears traces of this construction. When glaciers grind rock to fine powder, they produce what geologists call glacial flour, a dust of minerals so fine that it can stay suspended in water for long periods. When this powder entered the ocean, it acted as a source of nutrients, releasing iron and other elements that are essential for plankton growth. In regions where glacial meltwater met seawater, these nutrients fueled blooms of microscopic life, which in turn supported fish and marine mammals. The connection between ice and life was not just mechanical but chemical, a link between erosion on land and productivity at sea. In this way, glaciers shaped both the structure of the seabed and the balance of life above it. As the Ice Age waned and the glaciers began their long retreat, their architectural influence deepened. The melting ice released torrents of water that carved new valleys and deepened old ones. Meltwater rivers flowed beneath the ice as well as on its surface, forming networks of tunnels and channels that emptied into the ocean. When the ice disappeared, these channels became submarine valleys, some of which now serve as conduits for modern currents. In Greenland and Antarctica, scientists have traced such features for hundreds of kilometers, finding that they direct the flow of water under the ice shelves even today. The architecture built by ancient ice continues to guide the motion of the modern ocean. One of the most striking features left by glacial construction are the drumlins, elongated hills of sediment shaped by the flow of ice. On land, they appear as smooth, teardrop-shaped mounds that often occur in clusters, all pointing in the direction the glacier once moved. Beneath the sea, similar formations exist, though few ever see them. Sonar mapping reveals fields of submarine drumlins stretching across the continental shelves of northern Europe and North America. Each hill represents a moment of balance between erosion and deposition, between movement and stillness. Together they show the flow of ice as clearly as wind leaves ripples in sand. The ice was also responsible for creating the fjords that now define many high-latitude coastlines. These deep, narrow inlets were carved by glaciers that once filled entire valleys. The ice's immense pressure gouged the rock below sea level, and when the glaciers melted, seawater flooded in. Today, these fjords are among the most productive marine environments in the world, supporting rich communities of fish, birds, and mammals. Their steep walls and deep basins influence the movement of water, trapping nutrients and creating layers of temperature that sustain diverse ecosystems. The fjords are living monuments to the constructive power of ice, reminders that destruction and creation are often the same process viewed from different timescales. In many parts of the world, the influence of glacial architecture extends far beyond the visible coast. Beneath the North Sea, the Baltic, and the Gulf of Maine, the seafloor is crisscrossed with ridges and grooves carved by the advance of ice. These features affect everything from wave patterns to sediment transport. In some cases, they even determine the locations of modern fisheries, as currents concentrate nutrients along the ancient contours. The quiet architects of the Ice Age continue to shape economies and ecosystems long after their work ended. The stability of the seabed depends in part on these glacial structures. The layers of sediment left by ice rafting and meltwater flow form strong foundations in some regions and weak, shifting deposits in others. Engineers building undersea cables, pipelines, or wind farms must account for this hidden complexity. A ridge formed 10,000 years ago by a retreating glacier can still redirect the modern flow of water or anchor a bank of sand. A buried moraine can alter the chemistry of groundwater as it seeps toward the sea. The legacy of ice is practical as well as historical. The shaping of the seafloor by glaciers also played a role in stabilizing global sea levels after the Ice Age. The basins and ridges formed by ice movement acted as temporary reservoirs, trapping meltwater and slowing the rate of sea level rise. In some regions, these natural barriers held back water for centuries, creating vast inland seas that drained slowly into the ocean. The release of that water came in pulses, sometimes causing abrupt flooding of coastal areas. These pulses, known as meltwater events, are recorded in the sediments of the North Atlantic as layers rich in freshwater organisms. They show how the architecture of the glacial world influenced not just the shape of the seabed, but the timing of the ocean's return. Beneath the Southern Ocean, where the Antarctic ice sheet met the sea, similar patterns exist. There, vast ridges of sediment known as grounding zone wedges mark where the ice paused during its retreat. Each wedge represents centuries of stability followed by rapid collapse. The seafloor around Antarctica is covered with these features, forming a topographic record of the continent's shifting boundaries. As the ice advanced and retreated through repeated cycles, it built layer upon layer of these deposits, creating a complex landscape of rises and troughs. When modern researchers send submersibles to explore these regions, they see a terrain that looks almost like a sculpted desert, with dunes, ridges, and valleys, all created by the movement of ice and the sediment it carried. The influence of glaciers on the seafloor extends even into the deep ocean. During periods of maximum glaciation, icebergs drifted thousands of kilometers from their sources, melting slowly as they went. The debris they released accumulated as a thin layer across the abyssal plains, far from any continental margin. In the cores recovered from these depths, scientists find alternating bands of fine dust and dropstones, each marking a different pulse of iceberg activity. These layers, collectively known as ice-rafted debris, are one of the main tools used to reconstruct the history of the Ice Age. They show not only when glaciers advanced, but also how far their influence reached into the open sea. The quiet architect of ice did not work alone. Their designs were shaped by gravity, wind, and water all acting in concert. When the glaciers melted, the rivers that emerged carried away the products of erosion and spread them across the ocean floor. Currents reworked these materials, smoothing rough edges and redistributing them according to density and flow. Over time, the chaotic debris of ice became organized into patterns, layers, fans, and ridges that mirrored the slow order of natural processes. Even in apparent destruction, there was a kind of structure, an underlying tendency toward balance. In the centuries following the end of the Ice Age, as sea level stabilized and the climate warmed, the marks of glacial construction became the framework for new marine environments. Coral reefs grew along the edges of submerged moraines, kelp forests took root in sheltered basins, and fish found refuge in the valleys carved by ice. The seabed became a foundation for regeneration. The same forces that had once scoured the earth bare had also prepared it for renewal. The scale of this construction is almost impossible to grasp. The glaciers of the last ice age covered a third of the planet's land area and held enough frozen water to lower global sea levels by more than 100 meters. The sediments they moved amounted to billions of tons, enough to reshape the outlines of continents. Every grain of sand along a northern coast, every pebble on an Arctic seafloor, owes its place to the slow, relentless motion of ice. The transformation was not a single event, but a continuous process spanning tens of thousands of years. A planetary project carried out without noise or intent, only the steady application of pressure and time. Today, the remnants of that work lie mostly hidden, buried beneath newer sediments or covered by modern seas. Yet their influence persists in ways both large and small. The ridges and troughs left by glaciers direct the paths of currents that carry nutrients across the ocean. The mineral dust ground from mountain ranges continues to feed marine life through river runoff. The basins carved by ice serve as storage for deep water, influencing the planet's heat balance. Even as the climate changes again, the architecture of the Ice Age remains part of the foundation on which the modern ocean operates. The glaciers were builders without blueprints, shaping a world that would only reveal its full form long after their disappearance. Their work was slow, patient and silent, an art of pressure and release, of carrying and letting go. Every coastline, every seabed valley, every sediment layer owes something to their touch. The ocean floor we know today is their legacy, a record of what happens when cold becomes motion and motion becomes form. And as the Earth continues its cycles of warming and cooling, that legacy will not vanish. It will evolve layer by layer, reshaped but never erased. In the stillness of the deep, where sunlight never reaches, the structures built by ice remain. They do not move or speak, but they guide the water that passes over them, the life that settles on them, and the currents that circle the globe. They are the quiet architects of the Earth's memory, and their work continues every time a wave breaks on a shore that once lay under ice. The world that followed them, warmer, wetter, alive with colour, was built upon their design, as all worlds are built upon the remains of the one before. And though the glaciers have long since melted, the seafloor they shaped still holds their fingerprints, preserved in silence beneath the weight of the sea. As the glaciers melted and the ice retreated into the higher latitudes, the world began to change in ways that touched every layer of the ocean. What had been locked in ice for millennia now flowed freely across the continents, finding its way into the sea. The balance between salt and fresh water, between what was frozen and what was fluid, shifted with each season, each year, each melt. It was a rhythm both steady and unpredictable, a pulse that controlled the ocean's chemistry, its circulation, and even the breath of the planet. The rhythm of salt and fresh was not a simple cycle of freezing and melting. It was a global process, an exchange that determined how the Earth distributed its energy, its heat, and its life. At the height of the Ice Age, the oceans had been saltier than they are today. With so much water trapped in the glaciers, evaporation from the surface of the sea continued, but far less of that water ever returned through rivers or rain. Over thousands of years, the loss of fresh input concentrated the salts left behind, increasing the density of seawater and altering the way it moved. The cold temperatures further thickened the surface, allowing it to sink more readily at high latitudes. These denser waters filled the deep basins, pushing older water upward and driving a global circulation that carried nutrients and heat around the planet. This slow overturning of the sea, the great conveyor that moved from pole to pole, was one of the main forces shaping the Ice Age climate. It linked the salt of the sea to the temperature of the air and the cycles of the ice itself. When the world began to warm, that balance was disturbed. The melting of ice released vast volumes of fresh water into the ocean, particularly in the northern hemisphere where the great ice sheets of North America and Eurasia were concentrated. Rivers swollen with meltwater carved deep channels across the land and poured into the Atlantic and Arctic. The salinity of surface waters dropped and their density changed. In places where cold, salty water had once sunk to the depths, the influx of fresh water created a lighter layer that floated above it, slowing the vertical mixing that had kept the ocean in motion. The conveyor that carried heat northward weakened, and with it the climate shifted in abrupt and sometimes dramatic ways. One of the most striking examples of this happened near the end of the last Ice Age, around 12,000 years ago. As the North American ice sheets collapsed, an immense glacial lake known as Lake Agassiz formed in what is now central Canada. For thousands of years, this lake was held in place by ice dams, its surface rising with every melt season. Then, in a geological instant, the barrier gave way. Fresh water poured into the North Atlantic through the St. Lawrence Valley, flooding the ocean with low salinity water. The effect was immediate and global. Ocean circulation slowed, the transfer of heat to the north diminished, and temperatures across Europe and the North Atlantic region plummeted for over 1,000 years. This cold reversal, known to scientists as the Younger Dryas, was a reminder of how delicately balanced the rhythm of salt and fresh could be. A single pulse of fresh water could reset the climate of an entire hemisphere. The same dynamic played out in other forms across the world. In the southern hemisphere, as the Antarctic ice sheet began to melt, it released a steady stream of fresh water into the Southern Ocean. This influx altered the density structure of the surrounding seas, changing how deep water formed and circulated. The Antarctic Circumpolar Current, the great band of water that circles the continent, adjusted its flow in response. These changes influenced how carbon dioxide was exchanged between the ocean and the atmosphere. During times of stronger circulation, deep water rich in dissolved carbon rose to the surface and released its gases. During times of weaker circulation, that carbon stayed locked away in the abyss. The pattern of glacial melting determined not only sea level, but also the chemistry of the air that surrounded the planet. Salinity is a subtle but powerful driver of the ocean's behaviour. The difference between a salty and a fresh layer can be only a fraction of a percent, yet it can control whether water sinks or floats, whether it flows north or south, whether it carries heat or traps it. In the high latitudes, where the air was cold enough to freeze the sea itself, this balance was even more dynamic. When sea ice formed, the salt in the water did not freeze with it. Instead, it was expelled downward, increasing the salinity and density of the water just below the ice. This denser layer would sink, helping to drive circulation. When the ice melted in summer, the fresh meltwater created a lighter layer at the surface, stabilizing the ocean temporarily. The cycle of freezing and melting, of salt expelled and fresh returned, became a heartbeat that governed the flow of water across the polar seas. In some regions, this process created zones of extraordinary productivity. Where fresh meltwater spread across the surface, it trapped nutrients rising from the depths. Plankton flourished in the stable upper layer, taking advantage of sunlight during the brief polar summers. Their blooms fed krill, fish, and whales, forming the base of ecosystems that thrived in the shadow of the ice. Even as glaciers advanced and retreated, life adapted to the rhythm, timing its cycles to the availability of light and nutrients. The combination of salt and fresh created gradients that life could exploit, sharp transitions in temperature, density, and chemistry that became ecological boundaries. As the ice sheets melted more fully, the inflow of fresh water accelerated. Sea levels rose, flooding coastlines and reshaping the geography of the continents. The new oceans were not uniform. In some areas, like the North Atlantic, the surface remained relatively fresh and cold. In others, like the tropical Pacific, evaporation made the water saltier than ever. These contrasts drove powerful currents, as dense, salty water from the tropics flowed toward the poles, and lighter, fresher water returned toward the equator. The pattern of this exchange controlled the transport of heat around the globe, shaping the weather systems that still dominate the modern world. The interaction of salt and fresh water also influenced the chemistry of the ocean's deep layers. When the surface became fresher and less dense, it limited the sinking of oxygen-rich water into the depths. In some regions, this led to reduced oxygen levels and changes in the distribution of marine life. Species that required well-oxygenated environments were pushed toward the surface or toward areas where mixing remained strong. Others adapted to the low oxygen zones, evolving specialized metabolisms that could survive in chemical gradients where oxygen was scarce, but other compounds like nitrate or sulfur were available. These adjustments helped maintain ecological balance, even as the environment transformed. In places where melting glaciers met the sea, enormous plumes of sediment-laden water poured outward. carrying not only fresh water, but also the mineral dust ground from rock. This material fertilized the surface ocean, stimulating blooms of plankton that absorbed carbon dioxide from the atmosphere. The interaction of fresh and salty water thus had a cascading effect. It influenced currents, climate, chemistry, and life all at once. The rhythm of salt and fresh was not only about physical balance, it was about the exchange of energy between all parts of the Earth system. As the glaciers receded further, the pulse of fresh water became irregular. Some years saw large surges as ice dams broke, others brought slow, steady flows from melting fronts. Each surge left a signature in the sediments of the ocean. Layers rich in lighter isotopes of oxygen mark times when the sea was diluted by meltwater, while layers with heavier isotopes correspond to periods of greater salinity. These records allow scientists to reconstruct the timing and magnitude of meltwater events, showing that the rhythm of salt and fresh was rarely smooth. It fluctuated like a living system, responding to internal feedbacks and external forces. In regions like the Arctic, this pattern continues even today. Modern measurements show that the balance of salt and fresh water still plays a crucial role in regulating climate. The melting of sea ice and glaciers adds fresh water to the surface, while evaporation and freezing increase salinity elsewhere. The same delicate dance that governed the Ice Age ocean still operates, though now influenced by human-induced warming. The lessons of the past remain relevant because the ocean has not changed its rules. It still moves according to density, temperature, and salt, just as it always has. During the height of the Ice Age, the difference between salty and fresh waters also shaped the distribution of sea ice. In polar regions, brine rejection during freezing made the underlying water denser, causing it to sink and allowing more ice to form. In contrast, areas with steady inflows of meltwater formed thinner ice that melted quickly each summer. These variations influenced albedo, the reflectivity of the Earth's surface, and therefore the planet's energy balance. The areas that remained icy reflected more sunlight and stayed cold, while open water absorbed heat and encouraged further melting. The rhythm of salt and fresh thus extended into the realm of sunlight and temperature, linking ocean chemistry to planetary energy. In the Pacific Ocean, shifts in salinity and temperature affected patterns such as El Niño and La Niña, even in the distant past. During colder periods, the difference between eastern and western Pacific waters became more pronounced, altering the strength of the trade winds and the distribution of rainfall across the tropics. The rhythm of salt and fresh was not confined to the poles, it resonated throughout the entire ocean, influencing climate systems thousands of kilometers away. The expansion and contraction of ice sheets also affected how rivers delivered fresh water to the sea. As glaciers advanced, they blocked drainage systems, forming lakes that stored water for centuries. When the ice retreated, these lakes often released their contents suddenly, sending catastrophic floods into the ocean. Each of these events altered salinity patterns, sometimes triggering temporary slowdowns in ocean circulation. These episodes remind us that the ocean's equilibrium, though vast, is always sensitive to sudden change. Even the sediment record on the seafloor bears witness to the rhythm of salt and fresh. In core samples taken from the North Atlantic, thin layers of fine, light-coloured material alternate with darker, coarser bands. The lighter layers correspond to times when fresh water diluted the ocean, reducing the amount of carbonate produced by marine organisms. The darker layers mark periods of higher salinity and stronger currents. Together, they form a pattern as regular as a pulse, an echo of the oscillations that once controlled the Earth's climate. The interplay of salt and fresh water also shaped the sound and movement of the ocean itself. Layers of different density refract sound waves, creating zones where sound can travel farther or become trapped. Marine life adapted to these conditions, with whales and other animals using the layers as acoustic guides. The stratification created by salinity differences became part of the sensory landscape of the sea, influencing how creatures navigated and communicated. In coastal areas, The mixing of fresh and salt water created estuaries, transitional zones that became some of the most productive environments on Earth. During the melting of the Ice Age, as sea levels rose and rivers flooded their valleys, countless new estuaries formed. These were places where nutrients from land met the tides of the sea, creating nurseries for fish, shellfish, and birds. The legacy of that period persists today in the world's great deltas and bays, from the Amazon to the Thames to the Mekong. Each one owes its existence to the balance struck between the flow of rivers and the returning sea. The rhythm of salt and fresh was not just a physical phenomenon. It was an organising principle for the entire Earth system. It determined how heat moved, how gases were exchanged, how ecosystems formed and collapsed. It linked the melting of ice in the polar regions to rainfall in the tropics, the chemistry of the deep ocean to the temperature of the air above the land. Every fluctuation in that balance echoed through the climate, sometimes subtly, sometimes violently. When we look at the modern ocean, with its layers of different salinity, its currents and gyres, we are seeing the continuation of a pattern that began in the Ice Age and long before. The sea has always been a mixture of histories, of water that has melted, evaporated, fallen and frozen countless times. The salts it carries are ancient, drawn from rocks and rivers, recycled through life and time. The fresh water it receives is temporary, a visitor that will soon return to the cycle. The balance between them is never fixed, only maintained through constant motion. As the last of the great ice sheets melted and the planet entered the warmer phase of the Holocene, the rhythm slowed, but did not stop. The influx of fresh water diminished, the salinity of the ocean stabilized, and the great conveyor resumed a more regular pace. Yet the memory of imbalance remained in the layers of the deep. The chemical signatures of those meltwater pulses are still there, frozen in time, reminders of how a world can change when salt and fresh lose their equilibrium. The story of that balance is not one of competition, but of cooperation. The ocean's power comes from contrast, heavy and light, cold and warm, salty and fresh. Without those contrasts, there would be no circulation, no weather, no life as we know it. The Ice Age taught the planet how to move energy through differences, how to create stability from imbalance. Even now, the same laws apply. When glaciers melt, when rains fall, when evaporation dries the surface, the ocean responds with its quiet adjustments, shifting layers, rebalancing its chemistry, and continuing the endless rhythm that began long before humanity appeared to measure it. The sea still holds that memory. Every current, every tidal exchange, every layer of density is part of the same conversation between salt and fresh. It is a rhythm that defines the living world, even when unseen, even when slow. Beneath the surface, the balance continues to evolve, as it did when the ice ruled the Earth. And though the planet has warmed, the ocean still breathes to the same pattern, keeping time with a pulse that never truly stopped, only changed its tempo. Even as the cold tightened its hold and glaciers pressed down over continents, the ocean beneath the ice remained alive. It did not rest. The sea has never known sleep, even when the surface froze so hard that the sunlight could barely penetrate the blue-white crust. Life persisted in every layer, from the drifting snow of plankton in the shallows to the slow-moving creatures that crawled across the dark seafloor. The cold did not silence them. It simply slowed the rhythm, altered the pace, and shaped the forms that could endure it. The Ice Age was harsh on land, but the ocean found ways to adjust. In many places it even flourished. The temperature of the water dropped, but with that cooling came a denser mixture of nutrients. When the ice sheets scraped the continents, they ground rock into fine dust that was carried by wind and rivers into the sea. Each particle was rich in minerals, iron, silica, phosphorus, materials that microscopic organisms needed to survive. The cold, nutrient-heavy waters became fertile ground for life at the smallest scales. Where sunlight reached through cracks in the ice or open patches of water, blooms of algae filled the surface, feeding krill, copepods, and small fish. Those creatures in turn fed larger predators, and so the web of life continued, even in the dim and frozen world. In the high latitudes, the cycles of day and night stretched into months. The long darkness of winter covered the poles in silence, but beneath that darkness the sea did not stop moving. Deep currents carried oxygen and nutrients from one hemisphere to the other, sustaining ecosystems far from the reach of light. In summer, when the sun returned and melted the surface, a rush of productivity followed. Phytoplankton multiplied in astonishing numbers, colouring the water in shades of green and brown. Their brief explosion of life became the foundation of entire food chains. Seabirds, seals, and whales timed their migrations to these cycles, arriving with the light and departing when the ice began to form again. Even where the ocean lay sealed under permanent ice, life found a way. In the modern Antarctic, scientists have discovered microbial communities living hundreds of meters beneath the ice shelves, feeding on nutrients dissolved in the cold water or released from rocks below. Similar conditions would have existed during the Ice Age. Bacteria capable of surviving without sunlight used chemical reactions instead, drawing energy from compounds like hydrogen sulfide or iron. Tiny crustaceans grazed on the bacteria, and small fish hunted them in turn. The food web was delicate but complete. The absence of light did not mean the absence of life. It simply meant that life had learned to feed on the planet's inner chemistry rather than its outer warmth. In shallower regions near the ice edges, larger creatures thrived. Krill, shrimp-like crustaceans that fed on algae growing beneath the ice, formed dense swarms that could stretch for kilometers. These swarms became the foundation for much of the marine life in the polar oceans. Fish, seabirds, and whales all relied on them, following their migrations through the seasons. The blue whales that roamed the glacial seas may have been fewer than today, but they still moved through the southern and northern oceans, consuming tons of krill each day. Their movements helped distribute nutrients through the water column. Each time they dove and surfaced, they mixed the ocean in subtle ways, carrying elements from the depths to the surface. On the continental shelves newly exposed during the glacial maximum, life adapted to the cold, shallow seas that replaced the deeper waters. Many of these shelves were covered in ice for part of the year, then open to the sun during short summers. The organisms that lived there had to tolerate dramatic changes in temperature, salinity, and light. Bivalves, worms, and crustaceans burrowed into the muddy bottoms, surviving under the ice and emerging when meltwater returned. They fed on the organic material that rained down from above, dead plankton, algae, and the remains of other creatures. This slow fall of material, known as marine snow, was a constant presence, a quiet nourishment drifting through the darkness. Deeper in the ocean, far below the reach of sunlight or ice, life remained almost untouched by the changes at the surface. The deep-sea ecosystems that existed then were much like those that exist now. Communities built around hydrothermal vents, cold seeps, and the slow decay of organic matter. Tube worms, clams, and bacteria clustered around cracks in the seafloor, where chemical-rich fluids emerged from beneath the crust. These vent ecosystems depended on chemosynthesis rather than photosynthesis, drawing energy from the Earth's interior instead of the sun. Their stability over millions of years made them some of the planet's most enduring habitats, unaffected by the cycles of ice above. The midwater zones between surface and depth were filled with drifting organisms, jellyfish, squid, small fish, and the plankton that supported them. Many of these creatures performed daily migrations, rising toward the surface at night to feed and sinking back into the darkness during the day. This vertical movement transported carbon and nutrients through the ocean, connecting layers that otherwise remained separate. Even during the coldest periods, these migrations continued, though perhaps at a slower pace, guided by the faint glow of bioluminescence rather than sunlight. One of the defining characteristics of life during the Ice Age was its flexibility. Species that could tolerate wide ranges of temperature and salinity survived where others could not. Fish populations shifted their ranges, moving toward the equator as the poles froze over. In the Atlantic, cod and herring followed the edges of the ice, thriving in the nutrient-rich waters of the glacial seas. In the Pacific, similar patterns occurred with anchovies and sardines. The movement of these fish, in turn, influenced the migration of predators, seals, orcas, and seabirds that depended on them. The entire system adjusted, each part responding to the changing boundaries of ice and water. Coral reefs, sensitive to temperature and sea level, faced some of the greatest challenges. As the oceans cooled and retreated, many reefs were left exposed or drowned in sediment. Yet some survived by migrating downward along the slopes of continental shelves, following the lowering sea. When the water rose again after the glaciers melted, the surviving reefs grew upward, forming the foundations of the modern barrier reefs we see today. The structure of the Great Barrier Reef, for instance, includes layers of coral that date back to the late Ice Age, each one recording a stage in the slow dance between land and sea. The benthic communities, the animals that lived on or in the seafloor, were equally shaped by the glacial environment. In areas where icebergs scraped the bottom, disturbing the sediment, only the hardier species could persist. Starfish, brittle stars, and burrowing worms occupied these shifting grounds, ready to recolonize after each disturbance. In more stable regions, communities of sponges and corals flourished. The cold water favoured slow growth and long lifespans. Some deep-sea corals that began growing during the Ice Age are still alive today, their skeletons holding records of past ocean conditions in their chemical composition. The chemistry of the water played a constant role in shaping life's distribution. As the ratio of salt and fresh shifted, so did the concentration of oxygen and carbon dioxide. Some organisms evolved to take advantage of the higher oxygen content of the cold water, growing larger or developing more efficient metabolisms. Others adapted to low oxygen environments in the deep, where slow decomposition of organic matter created pockets of anoxia. The variety of adaptations that emerged during the Ice Age laid the groundwork for the diversity seen in the oceans today. Whales, among the largest creatures of that time, continued to move between hemispheres, following the cycles of productivity created by the melting and freezing of ice. Bowhead whales, specially adapted to the Arctic environment, fed along the edges of the pack ice, using their massive heads to break through frozen surfaces for air. Their migrations traced the boundaries between ice and open water, marking the transition zones that define the glacial seas. Other species like grey whales followed coastlines that are now submerged, feeding in shallow bays that later disappeared beneath rising seas. Their routes shifted as the continents changed shape, but their instincts for movement endured. Seabirds, too, adjusted their lives to the glacial rhythm. Species that depended on fish and krill nested along the exposed coasts and cliffs that bordered the ice. During the short summers, they gathered in vast colonies, raising their young in a world of cold air and bright light. When the sea froze over again, they dispersed to the open waters of the mid-latitudes, where they could find food year-round. The fossil record shows that many modern seabird lineages date back to this period, shaped by the challenges of the Ice Age environment. The connection between life and the physical processes of the ocean was intimate and constant. Each shift in temperature or salinity, each change in current or ice cover, rippled through the food web. The ocean was not a static environment, but a moving, breathing system, and life responded to its every motion. When fresh meltwater poured in, some species flourished in the new conditions while others retreated. When ice advanced, animals and plants followed the shrinking habitats, compressing into smaller regions of open water. The resilience of life lay in its ability to adjust rather than resist. Even microbes, invisible to the eye, played a critical role in maintaining balance. Bacteria broke down organic material that settled on the seafloor, recycling nutrients back into circulation. Other microbes captured nitrogen from the air trapped in ice and released it into the ocean, feeding the growth of plankton. The microbial world was the foundation of the ocean's endurance. It absorbed shocks, regulated chemistry, and kept the cycles of life turning, no matter how the surface changed. The diversity of life during the Ice Age was immense, though distributed differently than today. Tropical regions remained relatively stable. Their coral reefs and mangroves diminished but not destroyed. Temperate zones shifted back and forth between productivity and scarcity as the climate oscillated. Polar regions expanded, becoming engines of nutrient production that fed the rest of the planet. The cold concentrated life rather than eliminating it, forcing ecosystems into new configurations that proved remarkably efficient. One of the lasting effects of this era was the redistribution of species. As glaciers advanced, some populations were cut off from others, leading to isolation and eventual divergence. When the ice retreated, these separated lineages sometimes met again, bringing genetic diversity that strengthened species against future changes. The Ice Age, though harsh, acted as a crucible for evolution, refining the adaptability of marine life through cycles of stress and recovery. The deep ocean, largely insulated from the surface climate, served as a refuge during periods of extreme cold. Species that could descend into the stable depths survived when surface conditions became too severe. When the climate warmed again, they recolonized the upper layers, re-establishing ecosystems in newly opened waters. This pattern of retreat and return created continuity across ages. The ocean's ability to shelter life in its depths ensured that no glaciation could ever fully extinguish it. When the great ice sheets finally began to vanish for good, the productivity of the ocean surged. Rivers carried torrents of nutrients into the sea, and the mixing of fresh and salty water created fertile zones along the coasts. The food webs that had survived the cold now expanded into the warmth, diversifying and multiplying. The legacy of the Ice Age remained in the structure of the ocean itself, in its layered salinity, its currents, its chemistry. But life adapted to the new equilibrium as quickly as it had adapted to the old. Through all the cycles of freezing and thawing, advance and retreat, life in the ocean never stopped. It slowed, it changed shape, it moved with the currents, but it never ceased. The cold could cover the world, the ice could press down on the continents, the sunlight could vanish for months at a time, and still, beneath it all, the ocean continued its quiet work of living. The world above might have been frozen, but the world below remained in motion, carrying forward the continuity of existence that no amount of ice could break. Even now, traces of that persistence remain. In the Arctic and Antarctic, under thick shelves of ice, microbial mats grow on rocks where no light reaches. In the deep Pacific, sediments preserve the shells of plankton that lived and died during the glacial ages. In the genes of modern species, the adaptations that allowed survival in the cold remain encoded. The ocean remembers, not through thought or intention, but through the continuity of life itself. The Ice Age ocean was not an empty, silent expanse, but a living system, rich, intricate, and enduring. It was filled with creatures that learned to move with its slow rhythms and to thrive within its limits. The sea never slept, it only changed its tone. And when the ice began to loosen its grip, that same living ocean was ready to expand again, to fill the world with motion, colour and sound once more. When the last glaciers still held their ground and the seas were cold and restless, the air above them carried more than just chill. It carried the ocean's breath. The winds that moved over the Ice Age world were not only the result of temperature or pressure, they were shaped by the rhythm of the sea itself. Every current, every shift in salinity or warmth, every melting front of ice changed the texture of the air. The ocean spoke through wind. It was a voice too vast for language, but its message was clear in the way the planet moved, in the weather that swept from pole to equator, in the slow conversation between water and sky. The Earth of that time was defined by contrast. Cold poles and warmer tropics created enormous differences in pressure, and the atmosphere responded with strength. Jet streams, the narrow rivers of air that circle the planet, were displaced from where they are now, their paths bent by the expansion of ice and the cooling of oceans. The westerly winds that today bring rain to temperate regions blew farther south, and the polar easterlies strengthened, carrying fine dust from the continents across the frozen seas. That dust, minute fragments of rock and soil, fell into the ocean, enriching it with minerals that fed plankton blooms. The wind was a courier of nutrients as much as of weather. Over the North Atlantic, where the ice sheets of North America and Europe met the sea, storms formed with relentless regularity. The temperature difference between the frozen land and the open ocean fueled their power. These were not hurricanes in the modern sense, but vast cyclonic systems that lasted for weeks, circling across the northern hemisphere, redistributing moisture and heat. Each storm carried traces of the ocean it was born from, its salt, its humidity, its faint warmth, and released them as snow or rain across the continents. In this way, the ocean reached far inland, sculpting the climate of the Ice Age world through the medium of air. The sound of that wind, had one been there to hear it, would have been constant. Along the edges of glaciers where ice met sea, it would have whistled through cracks and over ridges, carrying the hiss of distant waves beneath. Over open water it would have roared, driving spray into the cold air and carving patterns on the surface. The ocean answered with its own motion, waves colliding against ice cliffs and sending vibrations through the water. The two were inseparable, air shaping sea, sea shaping air. The polar regions were the great engines of this exchange. As cold, dense air descended from the ice sheets, it met the warmer, moister air rising from the ocean. The collision produced powerful storms and endless circulation. In Antarctica, katabatic winds poured down from the interior, reaching speeds that could strip snow from the ground and send it far out over the Southern Ocean. These winds helped drive the circumpolar current, the vast belt of water that encircles the continent. In the Arctic, similar winds funneled between mountains and across frozen plains, influencing the direction of drifting sea ice. The ocean's voice in those winds carried across entire hemispheres. Further south, in the mid-latitudes, the interaction between sea and air produced patterns that still define the modern climate. Where warm and cold currents met, fog formed in dense banks that rolled for days. These regions were rich in life, for the same processes that created fog also brought nutrients to the surface. The wind stirred the upper layers of the ocean, mixing them and allowing plankton to thrive. The more the air moved, the more the sea breathed. The boundary between them was never fixed. It shifted with temperature, with season, with the balance of salt and fresh. As the ice melted and sea levels rose, the geography of the wind changed again. New coastlines redirected air currents. Bays and straits that had once been valleys became sources of moisture. The retreat of glaciers exposed land that heated quickly under the sun, creating thermal contrasts that further shaped wind patterns. The world's atmospheric circulation reorganized itself in response to the slow expansion of the ocean. Each change in water surface altered how heat was stored and released, and the wind adjusted to follow. The ocean and atmosphere were locked in a dialogue that continued without interruption, each shaping the other with every movement. Dust, carried by these winds, told part of that story. During the coldest periods, the air was drier and the continents more exposed. Vast plains of glacial sediment lay bare, and winds swept across them unhindered. Fine particles of ground rock were lifted into the air and transported thousands of kilometers before falling into the sea. This dust fertilized the surface waters, especially in the southern oceans, triggering blooms of phytoplankton that drew carbon dioxide out of the atmosphere. The process cooled the planet further, strengthening the very winds that had begun it. It was a feedback loop of enormous scale, all driven by the unseen conversation between ocean and air. The tropics, though far from the ice, were not untouched by this exchange. The cooling of the northern oceans displaced the equatorial rain belts, shifting the pattern of monsoons and trade winds. Regions that had once been lush became arid, while others received greater rainfall. The Atlantic circulation, weakened by fresh meltwater, changed the distribution of heat, and the wind carried those changes into every corner of the world. Even the deserts of Africa and Asia felt the pulse of the northern seas. When the North Atlantic cooled abruptly during meltwater pulses, the monsoons weakened, reducing rainfall and altering vegetation. When it warmed again, the rains returned. The rhythm of distant ice dictated the breath of tropical winds. In the Pacific, the vast expanse of water amplified these connections. The prevailing easterlies strengthened, pushing warm surface water toward the western side of the ocean. In the east, cold, nutrient-rich water rose to the surface in response, feeding enormous blooms of plankton. The same winds that shaped the surface currents also carried moisture to the continents, influencing rainfall from the Americas to Southeast Asia. When the winds slackened, the warm water shifted eastward, changing global weather patterns. These cycles, precursors to what we now call El Niño and La Niña, were already part of the Ice Age climate system. The ocean's voice in the wind carried messages that stretched from pole to equator, from the depths to the clouds. On smaller scales, the interaction between wind and sea produced local patterns that sustained ecosystems. Along the edges of the newly formed coastlines, where cold water rose to meet the sunlit surface, winds blowing parallel to the shore drove upwelling. These currents brought nutrients from the deep, feeding fish and seabirds in abundance. The same winds sculpted dunes on land, built barrier islands, and redistributed sediment along the coasts. Every gust that passed over the ocean carried a trace of its power onto the continents, blurring the distinction between land and sea. The soundscape of the Ice Age ocean must have been extraordinary. The groan of moving ice, the boom of waves against frozen cliffs, the hiss of snow swept across open water, all of it mixed into a single continuous noise. Whales added their low songs which travelled for hundreds of kilometres through the dense water, while seabirds cried above. The wind carried these sounds, shaping how they were heard. Over the open sea, the hum of distant storms merged with the steady rhythm of waves. Along coasts, echoes bounced off ice and rock. It was a world where the boundaries between elements were constantly redrawn by motion. The winds also served as agents of change for life itself. They transported spores, seeds, and microscopic organisms across vast distances. During the Ice Age, when land bridges connected continents, these airborne travellers often found new homes far from their origins. Even in the coldest times, when much of the planet seemed inhospitable, the wind carried the potential for renewal. Over the ocean, it spread plankton blooms from one region to another, ensuring genetic diversity across wide areas. The atmosphere was as much a medium for life as the water below. In the polar regions, the formation of sea ice created its own unique sounds and movements that influenced the air above. As the ice expanded, it trapped bubbles of air and salt crystals. When the ice cracked or shifted, these bubbles escaped with sharp pops, releasing tiny jets of brine and vapour. The cold air above the ice absorbed moisture from the openings in the surface, forming low clouds that drifted over the frozen landscape. These clouds reflected sunlight back into space, amplifying the cold, but they also trapped infrared heat, creating a delicate balance between warming and cooling. The interplay between sea and air was precise, a continuous negotiation that defined the climate of the era. As the ice retreated and open water spread northward and southward, the wind's tone changed again. It grew warmer, wetter, and more variable. Storm tracks shifted poleward, and rainfall increased over newly exposed lands. Vegetation returned to the coasts, anchoring the soil and reducing the amount of dust carried into the sea. The fertilization feedback that had helped maintain the Ice Age began to weaken. Carbon dioxide levels rose in response, and the planet warmed further. The same winds that had once carried the ocean's cold breath now carried its warmth. The cycle turned, but the relationship between air and water remained unbroken. Even in the midst of such slow transitions, the system never lost coherence. The winds that shaped the climate of the Ice Age continued to move according to patterns governed by the sea. Pressure differences, temperature contrasts, and the rotation of the Earth determined their routes, but the ocean provided the energy, the release of heat from the surface, the evaporation of water, and the condensation of clouds all tied the two systems together. The ocean's voice in the wind was not a metaphor. It was the literal exchange of energy between water and air, the process by which the planet maintained its balance. Over time, as sea levels stabilized and the great ice sheets dwindled, the winds settled into patterns closer to those we know today. But their memory of the glacial world persisted. The positions of modern storm tracks, the frequency of monsoons, even the distribution of deserts and forests, all bear the imprint of the Ice Age winds. The planet's atmosphere still carries the signature of that era, written in the way it moves heat and moisture around the globe. The connection between ocean and air, forged in the cold, remains the central mechanism of Earth's climate. The circulation of the atmosphere above the Ice Age oceans was both a consequence and a cause of the planet's rhythm. The cooling of the surface created pressure differences that drove the winds, and the winds in turn influenced how heat was stored and released by the sea. This constant feedback shaped the pace of deglaciation, the timing of rainfall, and the spread of vegetation. It linked every part of the Earth system into a single, self-adjusting whole. There were no separate domains of ocean and atmosphere. There was only one continuous flow of energy, manifesting as currents below and winds above. As the Ice Age drew to a close, this connection became even more apparent. The massive freshwater pulses that entered the ocean from melting glaciers disrupted circulation, and the atmosphere responded instantly. Weather patterns shifted, storm systems moved, and temperatures fluctuated across continents. The feedback between salt, temperature, and wind determined how quickly the planet would emerge from the cold. When the ocean began to release the heat it had stored, the winds carried it outward, distributing it across the surface of the Earth. The air, in a sense, became the ocean's messenger, translating its slow movements into the immediate language of weather. Even today, traces of that dialogue can be seen in the patterns of modern climate. The polar jet stream, the monsoons, the trade winds, all are shaped by the same principles that governed the Ice Age world. The difference lies only in scale and intensity. The ocean still speaks through the wind, though the tone has shifted with time. It is warmer now, more humid, and perhaps more unpredictable. Yet the underlying rhythm remains, unchanged since the first glaciers met the sea. If one could stand at the edge of an Ice Age coast and feel the air move, it would have told a story without words. The cold, dry wind descending from the glaciers would meet the moist, salt-scented breeze from the sea. Between them lay a band of mist and turbulence, the place where the ocean's breath became the atmosphere's motion. That boundary, invisible but real, was where the planet's energy exchanged hands. The sound of it, the feel of it, was the pulse of Earth itself, a constant living presence that never rested, not even when the world was frozen. As the planet continued its slow warming, that pulse began to quicken. The wind carried new moisture to new places, carving out the weather systems that would define the post-glacial world. Forests grew where tundra had been, rivers swelled, and rain fell in regions long dry. The atmosphere, always restless, followed the ocean's lead into this new balance. The Ice Age had ended, but the relationship it revealed between sea and sky remained the foundation for everything that came after. The wind still carries the ocean's memory, its sound and its breath, even now. When the balance finally began to shift and the long cold started to loosen its grip, the change was not sudden, but constant. The world did not melt all at once. It thawed in pulses, in small retreats followed by pauses in the slow rearrangement of air, water, and stone. Each year brought a little more warmth, a little more melt, a little more movement in the oceans and the skies. The planet was not waking from a deep sleep, so much as turning over, changing sides, seeking equilibrium. The moment of thaw was not one moment at all, but thousands, spread across continents and centuries, felt in the rise of rivers and the deepening of seas. The ice that had once covered a third of the Earth began to withdraw. In the northern hemisphere, the Laurentide ice sheet that had buried much of North America split apart and retreated toward the Arctic. In Europe, the great Scandinavian ice mass drew back from the British Isles and the plains of Germany and Poland. In the south, Antarctica shed the outer shelves that had once extended far into the Southern Ocean. As the weight of all this ice lifted, the land beneath it began to rebound, slowly rising back toward its former height. Valleys deepened, mountain ranges tilted, and rivers carved new paths to the sea. The crust of the planet, long pressed downward by frozen water, exhaled as the pressure eased. As the glaciers melted, the water they released found its way into every basin and lowland. Some flowed quietly, filling valleys and forming new lakes. Others came suddenly, as ice dams gave way and unleashed torrents that swept across entire regions. These outburst floods scoured the land, leaving behind immense channels, boulder fields, and layered deposits. In North America, such events carved features like the scablands of Washington and the basins of the Great Lakes. In Europe and Asia, they created plains and river deltas that would later become fertile ground for forests and human settlement. Each flood carried the memory of ice with it, transferring the story of the glaciers into the shape of the land. The oceans received all of this water, rising with each century. At first, the change was slow, millimeters per year, but over time it accelerated. The shorelines advanced inland, flooding river valleys and covering coastal plains that had once been grasslands. The great continental shelves, exposed for tens of thousands of years, vanished beneath the sea once more. The lowlands of Beringia, Doggerland and Sunda disappeared, transforming from dry plains into shallow seas. The continents resumed the shapes that would become familiar in the modern era, though still subtly different. The thawing ice did not just add water to the ocean, it altered its chemistry, its temperature and its movement. When fresh meltwater entered the seas, it created layers of lighter water that floated above the denser, saltier depths. These layers disrupted the circulation that had governed the ocean during the Ice Age. Regions that once produced cold, sinking water slowed, while others gained strength. The deep currents adjusted, redistributing heat around the planet. This reorganization took centuries, but its effects were global. Temperature gradients weakened, storms shifted, and rainfall patterns changed. The melting of ice was not only a local event, it was a restructuring of the entire climate system. As sea levels rose, coastlines changed from year to year. Forests that had grown along riverbanks were drowned and replaced by tidal marshes. In some places, the ocean advanced kilometers inland within a human lifetime. The sound of the waves changed as they met new shores, breaking on what had once been fields or hills. The ocean reclaimed its boundaries with patience, smoothing the edges of continents, washing away traces of the world that had existed under ice. The land did not resist. It adapted, giving way as it always had. The rising water also affected the salinity balance of the oceans. In high latitudes, the influx of fresh water reduced density, slowing the sinking of cold currents. In the tropics, evaporation intensified as temperatures rose, increasing salinity there. The contrast between these regions drove new circulation patterns that redistributed energy more efficiently across the globe. The ocean began to function less as a cold storage system and more as a conveyor of heat. This transition marked the true end of the Ice Age, not the disappearance of the last glacier, but the moment when the ocean's rhythm shifted to match a warmer world. On land, the retreat of ice revealed ground that had not seen the sky in tens of thousands of years. The newly exposed soil was raw and mineral-rich, covered with stones and fine silt left behind by the glaciers. Wind and water quickly began to shape it, forming dunes, streams and lakes. Mosses and lichens were the first to return, followed by grasses and shrubs. Animals followed soon after: mammoths, reindeer, bison, and the humans who hunted them. In these regions, the boundary between land and sea changed continually, and life followed it. Each generation saw a different map of the world, a reminder that the Earth's surface was always in motion. Beneath the ocean, the thaw had its own consequences. As the ice sheets retreated from continental margins, they left behind deep depressions filled with loose sediment. Water filled these basins, and currents reworked them into new forms. Submarine canyons extended their reach, carved by meltwater rivers that flowed beneath the glaciers. Fjords deepened and widened, becoming gateways between land and sea. In some places, methane that had been trapped in frozen sediments, hydrates locked by pressure and cold, was released into the water as the temperatures rose. These plumes of gas fed bacterial communities that colonized the seabed, creating ecosystems dependent on chemical energy rather than sunlight. The thaw awakened not only landscapes, but also ancient biogeochemical processes. The atmosphere responded quickly to the changing ocean. As water temperatures rose, the sea released some of the carbon dioxide it had stored during the glacial period. This release amplified the warming, reinforcing the feedback between ice, air and sea. The increase in greenhouse gases did not create the end of the Ice Age, but it accelerated it, ensuring that the transition would continue even without additional external forcing. The system had crossed a threshold, and the energy balance of the planet shifted toward a new equilibrium. In the high northern latitudes, the retreat of ice exposed vast areas of tundra and permafrost. During the Ice Age, these frozen soils had locked away organic matter, accumulated over millennia. When they thawed, microbes decomposed the material, releasing carbon dioxide and methane into the atmosphere. The contribution of these gases added another layer to the feedback loop of warming. The thawing ground became both a symptom and a driver of change, linking the deep earth to the air above. As the glaciers shrank, their surfaces became riddled with meltwater channels and lakes. These pools absorbed sunlight, darkening the ice and increasing melting even further. Rivers flowed across the ice and beneath it, carrying sediment and heat to the base of the glaciers. This internal melting caused the ice to slide faster toward the sea, increasing the rate of calving and discharge. The process fed on itself. More melting led to more flow to more melting. The glaciers that had once seemed immovable were now dynamic, their margins collapsing into the ocean in a rhythm of cracking and reforming. At the edges where ice met water, the transition was most dramatic. Enormous icebergs broke away and drifted into the sea, some as large as cities. As they melted, they released cold, fresh water and the debris they carried from the land. These floating islands of ice altered local ecosystems, shading the water below, changing salinity and depositing nutrients as they decayed. The release of meltwater plumes created zones of productivity that followed the paths of the icebergs. The ocean's surface, once a uniform sheet of cold, became a patchwork of contrasts: warm and cool, fresh and saline, stable and turbulent. This period of rapid transformation, known to scientists as the deglaciation, lasted for thousands of years, yet in geological terms it was abrupt. The sea rose by more than 100 meters, continents shifted their outlines, and ecosystems reorganized from pole to equator. For humans living at the time, these changes would have been visible but gradual, a lifetime span between shorelines. Generations would have grown up in one landscape and grown old in another, their migrations following the retreating ice or the advancing sea. The moment of thaw reshaped not only the planet but the trajectory of human history. The return of warmth brought back rainfall to many regions that had been dry for millennia. Rivers that had dwindled during the Ice Age swelled again, connecting lakes and valleys. The increased evaporation from the oceans fed larger storm systems, which redistributed moisture more evenly across the globe. Deserts retreated, grasslands expanded, and forests began to spread northward. In the tropics, monsoon systems strengthened, replenishing groundwater and rejuvenating ecosystems. The Earth's hydrological cycle quickened, moving more water through the atmosphere each year than it had during the frozen era. The planet was learning to circulate again. Marine life responded with equal dynamism. The influx of nutrients from melting glaciers and river runoff triggered massive blooms of plankton. These microscopic organisms multiplied in quantities unseen for tens of thousands of years, feeding zooplankton, fish and whales. The food chains rebuilt themselves in a matter of centuries. As temperatures rose, species that had migrated toward the equator during the glacial maximum began to move poleward once more, reclaiming habitats that had been lost to ice. Coral reefs resumed their growth, expanding along the edges of warming seas. The ocean, though changed in chemistry and structure, adapted quickly to the new equilibrium. Beneath the waves, the melting of permafrost and ice sheets altered the balance of nutrients and minerals in the water. Iron and silica released from glacial sediments fueled phytoplankton growth, while carbon from thawed soils contributed to the deep ocean carbon cycle. The mixing of these materials created a complex feedback between biological productivity and atmospheric composition. In some regions, the increase in plankton growth drew down carbon dioxide, tempering the warming slightly. In others, the decomposition of organic matter released methane and offset the cooling effect. The interplay between biology and chemistry was as dynamic as the melting itself. The transformation of the planet during the thaw also affected the appearance of the sky. As the atmosphere grew warmer and wetter, cloud cover changed. High-latitude regions that had once been dominated by clear, dry air developed persistent layers of low clouds that trapped heat. The distribution of aerosols shifted as dust storms became less frequent and sea salt took their place. The brightness of the atmosphere, its ability to reflect sunlight, decreased slightly, allowing more solar energy to reach the surface. This subtle change reinforced the warming, nudging the system further towards stability in the new, warmer state. In the midst of these vast processes, the planet remained balanced in its own way. For every glacier that melted, new lakes and wetlands formed to store water. For every floodplain submerged, a new coastal ecosystem emerged. Mangroves colonized the newly flooded shores, seagrasses spread across shallow bays, and coral reefs grew on submerged ridges. The rising sea created habitats as quickly as it destroyed them. The dynamic between loss and creation was constant, an ongoing adjustment that kept the biosphere resilient. In the far north and south, where ice persisted longest, the thaw was slower but inevitable. Even there, cracks opened each summer, widening a little more each year. Meltwater carved channels across the ice surface, flowing into deep crevasses and disappearing into the interior. The sound of this melting was continuous, a low, distant rush of water moving through a labyrinth of ice. These internal rivers carried heat downward, accelerating the process from within. The glaciers, though vast, were permeable. They absorbed their own undoing. The ocean, newly liberated from its frozen boundaries, expanded into the space left behind. Currents strengthened as global temperature differences decreased. The deep ocean circulation, which had been sluggish under the weight of cold, began to move more freely. Heat from the tropics spread more efficiently toward the poles, reducing extremes in climate. The pattern of this movement set the stage for the stable climate that would define the Holocene epoch, the period in which human civilization would eventually emerge. The moment of thaw was, in essence, the planet rebalancing itself. The ice had stored water, energy and carbon for tens of thousands of years. Its melting released them back into circulation, restoring the cycles that had been slowed by cold. Nothing in the process was wasted. Every droplet that ran off a glacier carried minerals to the sea. Every gust of warm air over melting ice transported moisture that would become rain elsewhere. Every flood carved a new path that life would later follow. The thaw was not destruction, it was redistribution. The world that emerged from it was different in nearly every respect. The outlines of continents had changed, the chemistry of the ocean had evolved, and the atmosphere carried new proportions of gases. Yet the same fundamental systems continued. The same currents, winds, and feedbacks that had sustained the planet through the cold now adapted to the warmth. The Earth had not escaped the Ice Age so much as transformed it into another mode of being. The remnants of ice lingered at the poles, reminders of what had come before, but the energy of the planet now flowed more freely. From a distance, it might have looked like a slow, patient recovery, but within the details it was a series of rapid adjustments. The Earth was constantly fine-tuning itself, searching for a balance between sunlight and reflection, between heat stored and heat released, between water held and water freed. The moment of thaw, stretched across millennia, was the recalibration of the entire planetary system. And though the ice continued to retreat, the ocean did not stop rising for thousands of years. Each new pulse of meltwater added to its depth, inch by inch, year by year. The coastline shifted endlessly, but life followed without hesitation. Fish colonized the flooded valleys, seabirds nested on new cliffs, and humans adapted to the encroaching tides. The ocean, in its quiet persistence, reclaimed what had once been its own, and the planet settled into the pattern that would carry it forward into the age that followed. The water that filled the oceans after the long thaw did not begin as something new. It was old water returning to motion, ancient in origin, carrying with it the memory of ice and time. Every molecule that rejoined the sea had already been part of countless cycles, frozen, melted, evaporated, condensed, and fallen again. The ocean that emerged from the end of the Ice Age was a record keeper, storing in its chemistry the evidence of every climate, every fluctuation, every trace of what had happened before. It remembered in layers, in temperature gradients, in the balance of salt and fresh, and in the sediments that settled slowly across its floor. When the glaciers receded and the rivers carried their melt to the sea, they also carried minerals from the rocks they eroded. Calcium, magnesium, potassium, and sodium. Elements freed by ice and time flowed into the ocean, adding to the mix of salts that define its composition. The exact proportions of these elements tell a story about the Earth's surface conditions. During glacial times, when chemical weathering slowed, the supply of certain ions diminished. During interglacial periods, it increased. The ocean, as a result, holds a chemical memory of the balance between rock, ice, and atmosphere. Its salinity is not static. It is a reflection of processes happening on land, thousands of kilometers away over spans of millennia. In the deep basins of the Atlantic and Pacific, the layers of sediment that accumulated after the Ice Age preserved a record of that transition. Each layer marks a shift in climate, a change in current, or a pulse of biological activity. The thickness, colour, and composition of these sediments vary with the planet's rhythm. Pale layers often correspond to times of low productivity, when dust rather than organic matter dominated the input. Darker layers mark times of abundance, when plankton flourished and organic carbon settled into the depths. Embedded within these layers are microscopic shells made of calcium carbonate, the remains of organisms that lived near the surface and sank after death. The isotopic composition of these shells holds precise information about the temperature and chemistry of the ocean at the time they formed. Scientists today can read those records with remarkable accuracy. The ratio of oxygen isotopes, oxygen 18 to oxygen 16, within a shell reveals the temperature of the water in which it grew. Higher ratios indicate colder conditions, lower ratios, warmer ones. By extracting and analysing cores of sediment from the seafloor, it is possible to reconstruct the entire sequence of glacial and interglacial cycles, tracing the planet's shifts over hundreds of thousands of years. Each centimetre of mud represents decades or centuries of time, and each grain is a piece of evidence left behind by the movement of water. The ocean's memory is written not in words but in chemistry, its script continuous and unbroken. Beyond temperature, the sediments record the movement of nutrients and carbon through the global system. When plankton grow, they draw carbon dioxide from the atmosphere and convert it into organic matter. When they die, a portion of that carbon sinks to the deep ocean, where it can remain trapped for thousands of years. The rate of this biological pump fluctuates with climate. During the Ice Age, strong winds and high nutrient levels in the Southern Ocean drove intense plankton blooms, which stored large amounts of carbon in the deep. When the world warmed and circulation patterns changed, that stored carbon began to return to the surface, where it was released back into the air. The memory of this exchange remains locked in the isotopic ratios of carbon within the sediments. It is through these chemical traces that we know how the Earth's carbon cycle has oscillated between ice and warmth. But the memory in the water is not limited to chemistry. It is also physical. The ocean is layered, with each depth holding water of a distinct temperature, salinity, and density. These layers can persist for centuries, even millennia, slowly moving through the global circulation system. A parcel of water that sinks in the North Atlantic today may not resurface until it reaches the Pacific hundreds or thousands of years later. In that time, it carries with it the chemical fingerprint of the surface conditions under which it formed. The deep ocean is, in this way, an archive of past climates. When scientists measure the properties of water at different depths, they're essentially reading pages from that archive, turning through the history of the planet as preserved in the movement of molecules. The concept of ocean memory extends to its currents as well. The pathways that water follows across the globe are influenced by the shape of continents, the position of mountains, and the depth of basins, features sculpted during the Ice Age. The ridges, valleys, and seamounts left by glacial erosion still steer the flow of deep currents today. As a result, the modern ocean circulates according to a design drawn thousands of years ago. The movement of heat, nutrients, and dissolved gases across the planet follows patterns established by the interplay of ice and time. Each current, each gyre, each upwelling zone is part of a physical memory encoded in the Earth's shape. The memory is biological too. Life in the ocean carries the imprint of glacial cycles in its genes and its distributions. Many species of fish, invertebrates, and plankton trace their evolutionary pathways to the pressures of the Ice Age. When sea levels fell, populations were divided by land bridges and shallow seas. When the water rose again, they mixed and diversified. Genetic studies show that many modern marine species experience population bottlenecks or expansions corresponding to these changes. The ocean's biodiversity is, in this sense, a living record of its climatic history. The patterns of migration, adaptation, and survival that define marine life today were set in motion by the rise and fall of ice. The sediments of the continental shelves contain another layer of memory, organic molecules known as biomarkers. These compounds, produced by specific groups of microorganisms, persist long after the organisms themselves have disappeared. By studying the types and ratios of these molecules, researchers can reconstruct details of past ecosystems, such as the dominance of certain plankton species or the productivity of algae during different periods. Some biomarkers even reveal the temperature of surface waters, as certain lipids adjust their composition depending on heat. Each molecule is a small, precise piece of history, a snapshot of the ocean's state at the time of its creation. In addition to the long-term records preserved in sediments and currents, the ocean holds shorter memories that influence its daily and seasonal behaviour. Temperature anomalies, salinity changes, and nutrient pulses can persist for years, shaping weather and climate patterns across the globe. events like El Niño and La Niña, which arise from the interplay between ocean and atmosphere, are examples of this kind of short-term memory. The ocean remembers its own fluctuations and carries them forward, influencing the next cycle. These memories are not static, they are dynamic, constantly updated by the motion of water and the exchange of heat. Yet they show that the sea has continuity, a capacity to retain and project the effects of its past into its future. The memory of the Ice Age also lingers in the very structure of the ocean basins. The weight of the ice sheets had pressed the Earth's crust downward, creating depressions that are still rebounding today. This process, known as isostatic adjustment, causes changes in sea level relative to the land. In regions once covered by thick ice, the land is still rising, while in areas at the margins of the ice sheets, the crust is sinking. These adjustments continue to alter coastlines thousands of years after the glaciers disappeared. The shape of the seabed reflects this slow recovery, recording in its contours the weight of vanished ice. The water itself preserves evidence of these transformations in its isotopic composition. The ratio of oxygen isotopes in seawater changes with the amount of ice on the planet. During glacial periods, more of the lighter isotope, oxygen-16, becomes trapped in ice sheets, leaving the ocean enriched in the heavier isotope, oxygen-18. When the ice melts, the ratio reverses. This isotopic signature remains in the ocean's chemistry for millennia, providing a means of tracing past volumes of ice and sea level changes. The ocean carries within it the record of how much water was once frozen and how quickly it returned. Even sound and motion act as forms of memory in the sea. The speed at which sound travels through water depends on temperature, pressure, and salinity. In the deep ocean, where these variables change slowly, sound can travel for thousands of kilometers without losing strength. This property allows scientists to monitor changes in ocean temperature by measuring variations in sound speed. The acoustic structure of the ocean is thus another kind of record, a reflection of its thermal history, constantly updated as the planet warms and cools. The biological remnants embedded in sediments also testify to the endurance of memory. Tiny shells of foraminifera, diatoms, and coccolithophores, organisms smaller than a grain of sand, cover vast areas of the ocean floor. Each species thrives under specific conditions of temperature and chemistry, so their abundance and diversity serve as indicators of past environments. By identifying the assemblages in each layer, scientists can reconstruct the shifts in climate, currents, and nutrient availability that occurred over time. The ocean's history is stored not in a single continuous narrative, but in billions of small, individual lives that once drifted in its waters. Some of the memory is invisible, but still measurable. The ocean absorbs gases from the atmosphere, and the concentration of these gases in the water depends on temperature, pressure, and biological activity. Traces of noble gases like argon, krypton, and xenon can reveal past temperatures, while concentrations of oxygen and carbon dioxide record the balance between photosynthesis and respiration. These chemical fingerprints persist long after the conditions that created them have changed. By studying them, it becomes possible to reconstruct the interactions between ocean and atmosphere that defined past climates. In coastal regions, the memory takes the form of buried landscapes. Beneath layers of marine sediment lie the remains of ancient forests, peat bogs, and river systems that existed before the sea rose. In some places, tree trunks still stand upright, preserved in anoxic mud, their wood darkened by centuries underwater. These submerged landscapes tell the story of how the world's edges moved during the thaw. They preserve pollen, seeds, and even footprints of animals and humans who lived along shores that no longer exist. The ocean holds these remnants in suspension between past and present, neither fully lost nor fully visible. The Arctic and Antarctic waters contain yet another form of memory, bubbles of ancient air trapped in sea ice and frozen sediments. When analysed, these bubbles reveal the composition of the atmosphere at the time they were formed, The rise and fall of carbon dioxide, methane and other gases are recorded in their concentrations, providing a direct link between the state of the ocean and the air above. Though most of the ice that held these records has long since melted, some remains in deep cores taken from the polar regions. The information extracted from them extends our understanding of the ocean's role in controlling the climate far beyond written history. The persistence of memory in water also influences how the modern ocean behaves. Because water retains heat so effectively, changes in temperature are not quickly erased. The warmth absorbed during the post-glacial period continues to circulate in the deep ocean, influencing the planet's heat budget even now. This thermal inertia means that the ocean acts as a buffer against rapid climate change, moderating shifts that would otherwise occur more abruptly. But it also means that the consequences of past warming persist long after their causes have faded. The ocean remembers every degree of heat added to it, carrying that memory forward in the form of expanded volume, altered currents, and changed chemistry. Every tide that rises against the shore carries the legacy of these ancient processes. The salts in the spray, the composition of the waves, the very density of the water, all reflect the accumulation of history. When rain falls and rivers flow into the sea, they continue the story, adding new chapters to the ocean's record. The boundaries between past and present blur, because the system never resets, it only continues. The water that circulates through today's currents has passed through glaciers, lakes, clouds, and living bodies countless times before. Each transformation leaves a trace, however small, that becomes part of the ocean's collective memory. That memory is not conscious, but it is precise. It holds the sequence of the Earth's transformations, encoded in molecules, sediments, and motion. When we study the ocean, we're not only observing what it is now, but what it has been. The depth, the temperature, the chemistry, all are outcomes of processes that began long before our species existed. The sea, in its vast continuity, remembers everything it touches. It holds within it the record of ice and warmth, of carbon and dust, of life and decay. And as it continues to move, it keeps adding to that record, one wave at a time, one current after another, carrying forward the unbroken memory of the planet's long history. As the warmth spread and the last fragments of the old ice withdrew toward the poles, the planet settled into a rhythm that felt almost steady. The long cycles of glaciation had left behind a world reshaped, but still recognizable, still part of the same slow continuity. The ocean filled the lowlands that had lain bare for so long, smoothing the scars left by glaciers, washing over valleys that had once held rivers, and redrawing the edges of every continent. The sound of the thaw faded into the steady pulse of waves, the same motion that had continued through all ages. The sea did not change its nature. It simply found new boundaries, new temperatures, new depths to inhabit. Beneath its surface, the history of the ice lingered in silence, stored in the sediments, in the salinity, and in the slow movement of its deep water. The air was thicker with moisture now, and rain fell more often than snow. The winds that once carried dust across frozen plains brought instead the smell of vegetation and the salt of the ocean. Rivers widened and deepened, feeding deltas and estuaries that spread where tundra had been. The sea crept inland, sometimes quietly, sometimes with force, shaping bays and lagoons, filling ancient depressions carved by the ice. The planet's colour changed as the white of glaciers gave way to green and blue. But beneath that transformation, the physical structure that the Ice Age had built remained, guiding the new flow of energy and life. In the Northern Hemisphere, vast forests took root on ground that had only recently been released from its burden. The soil, rich in minerals left by glacial grinding, supported thick growth that stabilized the land and altered the chemistry of the air. The trees drew carbon from the atmosphere, cooling the planet slightly and balancing the warming that the retreating ice had begun. This new vegetation also changed the way water cycled through the system. Evaporation increased, cloud patterns shifted, and rainfall redistributed itself across the continents. The ocean responded in kind, its surface salinity and temperature adjusting to the new input of fresh water from the land. The exchange between sea and sky continued, but the tone of that conversation was now warmer, calmer, and more humid. The polar regions, though still cold, no longer dominated the planet's energy balance as they had during the Ice Age. The reflective power of the ice diminished, and more sunlight was absorbed by the oceans. The currents adjusted accordingly. In the Atlantic, warm surface water flowed northward, replacing what had once been blocked by ice. This movement carried heat deep into the polar basins, moderating the climate of Europe and influencing rainfall across Africa and Asia. In the Pacific, the same processes stabilized the trade winds and encouraged the return of regular monsoons. The Earth was finding a balance that favored predictability over extremes. For the first time in many millennia, the seasons began to resemble those we know today. The deep ocean, too, adjusted to the new equilibrium. The dense, cold water that had formed under the ice during the glacial maximum continued to circulate, slowly rising in some regions and sinking in others. This deep circulation redistributed heat and nutrients across the globe, linking distant seas through a single continuous motion. The water that sank near Greenland might not reappear at the surface until it reached the southern Pacific, centuries later. In this way, the memory of the Ice Age persisted in the ocean structure. The water carried the chemical and thermal imprint of a colder world, blending it with the warmth of the new age. Marine life expanded into the spaces opened by the retreat of ice. Whales migrated farther, following new feeding grounds that had appeared in the warming seas. Fish populations grew in number and variety, adapting to changes in temperature and salinity. Coral reefs, dormant for thousands of years along the continental margins, resumed growth as sea levels stabilized, forming the foundations of the modern reefs that now circle tropical coasts. The abundance of life increased not suddenly but steadily, as ecosystems adjusted to the gentler climate. Every rise in temperature brought a corresponding rise in productivity, until the oceans reached a balance between new warmth and old nutrients. On land, the melting of glaciers continued to influence the oceans indirectly. As ice retreated from mountains and valleys, it released sediment that rivers carried to the sea. These sediments built deltas and coastal plains, creating shallow habitats that teemed with life. The minerals washed from the land fed plankton in coastal waters, strengthening the connection between continents and oceans. Even after the last remnants of the great ice sheets had vanished, their influence persisted in every river system, every estuary, every grain of sand that entered the sea. The relationship between land and water that had begun under the pressure of ice continued through the gentler work of rain. The climate that followed the Ice Age was neither static nor entirely predictable. The planet experienced brief fluctuations, intervals of cooling and warming that reminded it of its capacity for change. The Younger Dryas, the short return to cold that followed the Great Melt, had ended, but other minor oscillations followed. Each time the balance shifted, the ocean adjusted in turn, absorbing or releasing heat, altering currents, and modulating rainfall. The sea acted as the stabilizing force, its vast heat capacity smoothing out the extremes of air and land. The ocean's inertia became the planet's safety net, ensuring that the shifts that once came in violent surges now unfolded more gradually. This new stability gave rise to conditions that supported expansion of life on land, including humans. The warmer climate allowed agriculture to develop, and the steady rainfall patterns supported settlement. Rivers fed by the remnants of glacial melt provided fertile valleys, and the ocean's temperate influence moderated the seasons. Civilizations would eventually grow along these coasts and deltas, unaware that their stability rested on the equilibrium established by the slow retreat of ice. The planet that humans inherited was the product of tens of thousands of years of adjustment between sea, air, and land, a balance that could not have existed without the ice that came before it. Even as the Earth warmed, the polar regions retained their frozen caps. They were smaller than their Ice Age ancestors, but still immense, and they continued to shape global circulation. Each winter, new sea ice formed, and each summer it melted back, maintaining a steady exchange of energy with the atmosphere. These seasonal rhythms became part of the planet's breathing pattern, regulating temperature and ocean currents. The modern distribution of climate zones, tropical, temperate, polar, emerged from this steady alternation between freezing and thawing. The world had not escaped the reach of ice. It had simply learned to live with it in moderation. The water that now filled the oceans carried within it the full history of these transformations. The composition of the salts, the ratio of isotopes, and the temperature gradients all preserved evidence of how the planet had changed. The ocean's currents, shaped by the contours of glacial erosion, continued to follow paths carved by ice. The animals that inhabited it bore genetic traces of migrations forced by past cold. Even the winds that moved above its surface carried patterns established in the glacial world. The memory of the Ice Age remained embedded in every part of the system, not as a relic, but as a foundation. As centuries passed, the Earth's balance remained remarkably stable. Small fluctuations in solar radiation and orbital cycles continued to influence temperature, but the ocean's vast reservoir of heat dampened the effects. This stability allowed ecosystems to evolve and humans to thrive, building societies along the coasts that had once been the frontiers of ice. The ocean continued to rise slowly, a few millimeters each year, as glaciers in mountain ranges melted at a gentle pace. The process was too slow to notice, a continuation of the same thaw that had begun thousands of years before. The planet was not static. It was in a state of continuous, almost imperceptible motion. The ice that remained still played an essential role in this equilibrium. It reflected sunlight, kept the poles cool, and maintained the gradient that drove the circulation of air and water. The melting that occurred each summer was balanced by the freezing of each winter. The sea level stabilized, the salinity reached a new steady composition, and the great conveyor of ocean currents continued its slow rotation. The Earth for a time existed in a kind of quiet balance, neither advancing toward another glaciation nor retreating into unchecked warmth. It was a pause between extremes, long enough for life to build upon. In the depths of the sea, however, the memory of the cold still moved. The deep waters that had sunk during the final centuries of the Ice Age were still circulating, carrying their chemical and thermal signatures with them. In some regions, these ancient waters have only recently resurfaced, releasing their stored carbon and heat into the modern ocean. The memory of the last glaciation is not confined to geology or sediments. It is present in the very molecules of water that continue to travel through the global system. The ocean, in this way, still contains fragments of the Ice Age within it, moving quietly beneath the surface. Even the distribution of life in the ocean today reflects that continuity. The species that survived the glacial period adapted to its challenges and expanded again in the warmth that followed. Some lineages of plankton that first evolved under cold, nutrient-rich conditions continue to dominate polar waters, their physiology unchanged for tens of thousands of years. Deep-sea corals that grew during the transition still live on slopes and ridges, their skeletons preserving the chemical signatures of the ancient water in which they formed. The ocean is not divided between past and present. It is a single continuous system in which both coexist. The climate that emerged after the thaw was more complex than it seemed. While global temperatures stabilized, local variations remained significant. Some regions warmed quickly, others lagged, and the interaction between these differences shaped the evolution of weather patterns. The sea moderated these contrasts, transporting heat where it was needed and absorbing excess energy where it was abundant. The process created the relative mildness that allowed civilizations to arise in the mid-latitudes. The winds, guided by the same oceanic gradients, carried moisture to the continents in predictable cycles. The balance between land and sea, frozen and liquid, had finally reached a state that favoured consistency. In the farthest reaches of the ocean, where the deep currents still circulate through trenches and basins, the temperature remains close to that of the ancient cold. There the memory of the Ice Age persists as a physical condition, as the baseline of the planet's thermal structure. Every layer of water that rises from the abyss carries a trace of that ancient chill, a quiet reminder of the time when the world was encased in ice. The ocean's role as both archive and regulator continues, shaping the surface climate even now. The cycle that began with the accumulation of ice and ended with its retreat did not disappear. It only slowed. The processes that govern glaciation are still active. Shifts in the Earth's orbit, changes in solar radiation, variations in atmospheric composition. The stability of the present is temporary, just as the Ice Age once was. The difference lies in the scale of time. For the moment, the planet rests in a warm interlude, one of many that have punctuated its long history. The ocean continues to carry the heat of this period, storing it in the depths, balancing the climate as it has always done. If one were to trace the story of the Earth through its oceans, it would not appear as a series of separate eras but as a single continuous flow. The Ice Age, the thaw, the warmth that followed, they are not distinct chapters but different movements of the same process. The water that covered the planet before the first ice formed is the same water that covers it now. It has circulated through every phase, carrying the imprint of each. The sea remembers because it never stops moving, never stops exchanging, never stops adapting. It has seen the planet cold and it has seen it warm, and through all of it, it has remained the medium through which life endures. In the present, the remnants of that frozen past are still visible. The glaciers in Greenland and Antarctica, the ice caps in the high mountains, the permafrost in the Arctic soils. They are not relics but active participants in the same system, storing water, reflecting sunlight, and maintaining the temperature gradients that drive circulation. The world's balance still depends on them, as it always has. The ocean, for all its warmth, still listens to the rhythm of ice. And though the planet has changed beyond recognition since the height of the last glaciation, the connection between ice and ocean, between cold and motion, remains unbroken. The sea carries the lessons of that age within it, encoded in every current, every chemical signature, every layer of sediment. The glaciers may have retreated, but their influence persists in the way the Earth breathes, the way it moves heat, the way it sustains life. The sea, as it always has, continues its slow circulation, the great conveyor of memory and renewal, carrying forward the legacy of all the ages that came before.